Hello, can you guys hear me? Hi, everyone. Welcome to join our CVPR 2020 workshop on adversarial machine learning in computer vision. My name is Sihan Xie, and I'm co-organizing this workshop with Xingyun Chen, Songbai, Bo Li, Kaiming He, Feifei Li, Luke Wangu, Backdoor, Dan Song, and Alan Yu. Our workshop is sponsored by DeepMind. Before we get started, here are a few tips for better attending this workshop. First, we are recording the whole event. So after this workshop, we will make the video publicly available. Second, all audience are muted by default. But during the panel discussion, we will unmute some audience to let them ask questions. Third, please do not turn on your video during the workshop. For asking questions during the workshop, we provide two ways. The first way is directly using Zoom. You can click the chat button there and ask anything you want. The second way for ask question is by using Slido. The link of Slido can be found at the external website of our workshop. You can ask and vote your questions there. So let's move on to the main content of this workshop. We all know that deep learning is pretty successful in computer vision. For example, we have two very popular datasets in computer vision. One is ImageNet classification dataset, and another is Pascal detection dataset. But in the old days, these two datasets are pretty challenging for computer vision researchers. For example, without using deep learning on ImageNet, the best result is only 74.2 top 5 accuracy. And for Pascal object detection dataset, the best results is only 40.9 mean average precision. But with deep learning, this result can get greatly improved. For ImageNet, the state-of-the-art model now can get 98.7 top 5 accuracy. And for Pascal detection dataset, the state-of-the-art result is 90.5 mean average precision. However, deep learning models are not perfect yet. They still have a lot of problems. The first well-known weakness is that they are fragile to adversarial attacks. It is worth noting that adversarial attacks not only can happen in the digital world. Researchers also show that such attacks can reliably fool deep learning models in the real world. Besides adversarial attacks, deep learning models are also poorly generalized to images that may not well covered in their training dataset. For example, the challenging outdoor conditions such as fog, rain, and snow may cause troubles to self-driving cars, as these weather conditions are not well covered in the current self-driving training dataset. Deep learning models are also very sensitive to occlusion, which is a fundamental aspect of nature images. As shown in these examples, there are a lot of cars here there, but deep learning models can only able to detect 3 of them. In today's workshop, we bring non-experts on discussing these problems from the perspective of adversarial machine learning. They are Professor Alan Yu from Johns Hopkins University, Professor Alexander Madry from MIT, Professor Jelens Flanders from UW-Medicine, and Professor Matthias Besky from University of Tübingen, Dr. Lauren van der Metten from Facebook AI Research, Dr. Pingyu Chen from IBM, Professor Chuhui Xie from UCLA, Dr. Boqing Gong from Google, and Professor Thomas Dietrich from Oregon State University. Our workshop is a full-day workshop and is divided into 2 sessions. In the morning session, we will first hear the talks by Professor Alan Yu, Professor Alex Madri, Professor Yerens Fernandez, and Professor Matis Besky, followed by our panel discussion. And then is the poster session. Please note that all accepted papers will be presented in the poster session. In the afternoon, we will hear the talks from Dr. Lawrence Wadamaton, Dr. Pingyu Chen, Professor Chuhui Xie, Dr. Boqing Gong, and Professor Thomas Dietrich, and followed by the panel discussion. Similarly, after that, we will have the poster session. Here, all papers will be presented there. Next, I will briefly talk about the submission statistic of our workshop. We received a total of 47 submissions, and most of them you can see in this bar chart lying in the adverse attack and defenses. Out of these 47 submissions, we accept 24 of them, with 11 papers on attacks, 6 papers on defense, 1 paper on application of adversarial machine learning, 1 paper on representation learning, 2 papers on explainable AI, 2 papers on theoretical adversarial machine learning, and 1 paper on GAN. Next, we will announce the best paper award of our workshop. Our workshop is sponsored by DeepMind. First, we are excited to announce that improving the affordability of robustness training for DNNs won the DeepMind Best Paper Award. The authors are Siddharth Gupta from UIUC, Parajat Dubey from IBM Research, Ashish Verma from IBM Research. Please join me on congratulating these authors. Next, for the DeepMind Best Extended Abstract, the award paper is on certifying robustness against the backdoor attacks while randomized smoothing. The authors are Binghui Wang, Xiaoyu Cao, Jinyuan Jia, Neil Gong, all from Duke University. Again, please join me on congratulating these authors. We also have selected 8 people for travel award for covering their CVPR registration fee. There are Tianfu Wu from NCSU, Natia Ruz from Boston University, Jiawei Chen from Boston University, Sarwanti Adapali from Indian Institute of Science, Quentin Bonillo from CEA List, Jia Chen Sun from Michigan University, Kartik Gupta from Australian National University, Li Gonghan from Rutgers University. Lastly, on behalf of the organization committee, I want to say thanks for our amazing program committee. Thank you so much for your efforts on reviewing papers. So let's begin our workshop. Our first talk is by Professor Alan Yu. Alan Yu is a Bloomberg Distinguished Professor at Johns Hopkins University with appointment in both Cognitive Science Department and Computer Science Department. Dr. Yu completed his PhD degree at Cambridge University, supervised by Stephen Hawking. His computer vision research has been widely recognized and cited, winning several prizes, including Mar Prize. The title of this talk is Defending Against Random Occluder Attacks. Hi, Alan. You can share your screen now, and the floor is yours. Let me first turn off my.
Okay, so I'm on. This will stop other screen sharing? Yes, I guess that's okay. Yeah. And I think, can you see my screen?
Oh yeah, we can see your screen now.
Okay, so yeah, well, thank Chihang and the other members of the committee for inviting me to speak. I guess people give me feedback if I'm not talking loud enough or possibly talking too loudly. So the title is Defending Against Random Occluder Attacks, but actually a lot of my talk is going to put this in some degree of context. So the plan of the talk, part 1 will be brief history of performance evaluation, the infinite space of images, and perceptible adversaries. Part 2, infinite space of images, yet again, domain transfer and combinatorial complexity. And then part 3 will be on random occlusions and defending against them. And I guess the main point of my talk, which I think probably many people in this audience would agree, is that adversarial attacks are critical for dealing with the infinite space and the combinatorial complexity of real world images. So when adversary attacks started, I thought maybe there was sort of like a small fringe area that would never happen. But the more I thought of it, the more I thought that they were really critically important for vision. And if you don't already agree, I hope I'll persuade you about that during the talk. So here's part 1. This gives a bit of history. So brief, so when computer vision started in the late 1970s and early 80s, conferences, CVPR founded, all the other conferences came on a little bit later. If you worked in the subject, you were happy if your algorithm worked on a few synthetic images. And that was enough to get your papers published. However, then reviewers got a little bit tougher in the late 80s, and you now had to show that your algorithm worked on a few real images before they would publish it. Okay, then for most of the audience, maybe all of them, then benchmark datasets were created in the late 1990s and early 2000s. And this led to the standard paradigm where you have balanced finite size test and trained datasets plus some validation set. And so this was backed up by some nice sort of mathematics, probably approximately correct theory and so on, and general thoughts in computer vision. But is this right? Is this the way we should be evaluating algorithms? Has history of performance evaluation ended, like the historian Francis Fukuyama suggested in 1992? And I'd suggest no, that like that historian, history has not ended at all. It's changed. And that in computer vision, we should move to a new phase where we try and test our algorithms by adversarial attacks and test on infinite data sets while only training on a few images. So infinite space of images, so images, infinite space, you have a training set, you have a test set, finite size. Is that enough? Well, I think even 15 years ago, 20 years ago, there was some realization that this wasn't enough. And I'll mention the idea of hard negative mining. And again, to give a little bit of history, by the late 1990s, AI systems could defeat Kasparov at chess, but computer vision researchers couldn't detect objects in images, which was rather embarrassing. But in the year 2000, Paul Viola gave a live demo of face recognition at NIPS, or neural NIPS. And how? Well, Paul used machine learning algorithms, cascades of AdaBoost, which were trained with positive and negative examples. But that was not enough. You also needed hard negative mining. The point being that the set of positive examples was big enough because faces don't really vary very much. Your set of negative examples was not. If you wanted to detect faces in real images, your set of negative examples had to be big enough to include the near misses, image patches that occur in real images that look like faces but aren't. So hard negative mining, augment your set of false negatives by including false positives you get, and keep growing your data set by having more and more, by carrying on doing hard negative mining. For myself, I experienced this on work in text detection, which we're working on to help the visually impaired. And having seen Viola's talk, I realized that the methods he used were very useful for text detection. And so we could train and test, and we had a paper in CVPR 2005 about doing this. But really, to get it to work so that you could walk down, walk through New York City, top right, and have some system that would find text in real time, you couldn't just rely on a fixed size annotated data set. You had to make your set larger and larger and larger. So you can use hard negative mining to find near misses. Here are a few of them for text. things that, you know, might be text if you don't look too closely, and also hard positive mining to reduce false negatives. So you really had to keep growing the data set by working on real images and seeing where it broke down. Now, a general point which comes up, and I guess a lot, you know, this perspective will come out in Alexandra Madri's talk if he's discussing this aspect of his work, but data sets really consist of islands in the vast infinite dimensional sea of real images. The space of all images is infinite, so our finite sized data sets are only an infinitesimal fraction of the set of images. Now you can address this to some extent by the idea of adversaries, perturbative and imperceptible, which is for me somewhat in the spirit of hard negative mining. And the concepts of the min-max criterion due to Madri and others, you know, in terms of the metaphor, it means that the islands are given territorial waters. Each data point turns into a sphere of radius r, etc. So you are learning to populate this infinite sea, even though you've got a finite set of samples. And so there's a large literature on this aspect, which I won't really address, but here is, I guess, my first point about infinite dimensional space of images and the values of adversaries for exploring it and dealing with it. So now a second point about infinite spaces of images. So data sets for the same visual task can be very different. So one of the earliest data sets in computer vision, annotated, certainly the earliest for edge detection, was the Sowerby data set on the left, which was images of the English countryside, which had roads, but a lot of vegetation. So the background was heavily textured. On the right-hand side, another data set was South Florida. The images were taken indoors. They're very clean. There's no background texture. There's a Berkeley data set for people interested in the history, but that came along after these ones. So edge detection was much more difficult on Sowerby than on South Florida because there was so much background texture, and a standard edge detector like Canny would be terrible on it. It will be finding edges all over the place. So domain transfer, so this led to a domain transfer problem, how to get an edge detector that's trained on Sowerby to work on South Florida and vice versa. And so the first learning-based attempt to do edge detection, which was due to Scott Kanishi, a student of mine who was at Berkeley, was by chance also possibly the first to perform domain transfer, to the best of my knowledge. And I really like it if anyone knows anything else, because any other earlier example. His detector was able to do this because of details about how he went about it. He was trying to learn distributions for features, image features on edges and in the background. And then he could use log likelihood ratio tests to classify and to do edge detection, effective on both data sets. But he was also able to do transfer. Okay, why? The key idea was that there was a target you were trying to find, which were the edges, and the statistics for the feature responses were fairly similar on both data sets, because edges are edges. The statistics of the background were very different, because Sowerby had a lot of texture and South Florida did not. On the other hand, most of images are not edges. So if you want to estimate the background, you can do it without any annotation. You just do the statistics on everything in the image. It's a bit contaminated. It doesn't matter. So it struck me as domain transfer became hot again that in fact, we had actually published a paper on it, or Konishi had published a paper on it 15, 20 years ago. But it's an important problem, remains a really extremely important problem, I believe. So different data sets to get another type of metaphor, for the imperturbable, the original adversaries, non-perturbative ones, you have the metaphor of islands in a vast infinite dimensional sea. And for different domains, you've got a tribal metaphor. You have a large number of isolated tribes separated by mountain ranges and jungle with different languages and customs. So take Papua New Guinea, which is slightly larger than California. There are at least 312 tribes and 832 languages. So will findings on one tribe generalize to other tribes? Well, you don't know. You have to do the experiments and find it. And this is really important in practice, not only in sort of computer vision or natural images, but for computer tomography. Different hospitals take CT scans using different types of scanners, different protocols for different purposes. So you've really got a whole tribal set of different data sets, and do algorithms that work on one data set taken by JHU Hospital in the radiology department, work on data sets taken in the Harvard Medical School? The answer is often not, because the domains are different and transfer has to happen. So, you know, what's happening here really is that, you know, again, with this infinite sea of images, within it, there are sort of different oceans, sub-oceans, which are the different domains, and we need to deal with those as well as dealing with the individual seas themselves. Here's domain transfer again. Here is images of horses. You want to do pose detection. Here is two computer graphics images of horses. Here are line drawings of horses. Here is pop art of horses. Here's real images of horses. We want to have algorithms that will not just work on the real images, they'll work on the pop art, they'll work on the line drawings, they'll work on the computer graphics. And there's a paper by Jiting Mu about this. There's a literature on this, and there's a recent work on that, which I might mention if you're interested. So now, data sets. Now the third point about them is also exponentially and combinatorially large. So is any data set big enough to be representative of the real world? How many images should a data set have? People ask me questions about that, and my honest answer is I say, I don't really know. You have to make a data set, then you have to try to generalize it, etc. But here is a thought experiment from a paper we did a few years ago. Suppose the images are generated by a computer graphics model, I'll show in the next slide, and the image from computer graphics, it's caused by several factors: the geometry of the object, the texture and material properties of the object, the lighting conditions, and also, to some extent, the background surrounding the object. And so a quick study shows that you get an exponentially sized data set just for a single object. So any finite sized data set represents only an infinitesimal fraction of reality. And so great performance on any fixed data set like ImageNet does not guarantee good performance faced with the complexity of the real world. And to go back to quote Shakespeare, I could be bounded in a nutshell and count myself king of infinite space. Within my nutshell, localized nutshell, everything works well, but does it work outside the nutshell? I don't know. So here is just the illustration of that: images from synthetic computer graphics models, lighting, viewpoint, and here for this thought experiment, there were 4 parameters: lighting, 4 parameters for this, light sources, type, etc., texture, only one type of texture, only one type of material, scene layout, okay, 3 variables, total of 13 variables generating the image. And so you allow 10 to the 3 possibilities for each parameter listed. Well, you get 10 to the 39. And so this is just for a single object with background. And this obviously is a data set that's completely impossible for us to have at the moment, and even in the conceivable future. And this is for one object only. Of course, many of the images in this thought experiment are going to look so similar that you can probably reduce the amount, but still, this isn't intended to sort of make you think about that. Okay, data sets are combinatorially large. Well, that situation becomes even worse if you have multiple objects in a visual scene. You can generate a visual scene by selecting objects from the set of all possible objects, which is estimated at being 20,000. You place them in random positions. This easily gives you a combinatorial number of images. So, and suppose you just, you reduce this and just consider occlusion alone, the same argument goes through. You can occlude any object in a combinatorial number of ways. And here are some examples that I think Xiang created. You occlude the penguin with a television set. The deep network, at least the deep network at that time, thinks that the penguin is now a human. You occlude the monkey with a guitar. The deep network, at least at that time we did it, thinks that the monkey is a human and thinks the guitar is a bird. So large number of ways of doing, of occluding objects, and from these types of experiments, they can certainly affect the deep network. So occlusion, and maybe people don't think about this, I would say is also a type of attack. There are infinitesimal perturbation attacks, the standard type of attack that came up. There are patch attacks, which we'll hear more about by other speakers in this meeting. But I think there's also occluders, somewhat similar to patches, should be considered a type of attack, and there's a great deal of them, and they happen in many world situations, even if they don't happen very much in benchmark data sets. Okay, so this raises me, and I guess others, to think of, what does this mean? Current ways that we evaluate and train and evaluate algorithms are based on finite size data sets which are balanced. But if the world is combinatorially large, infinite sets of images, infinite, large numbers of different domains, combinatorial numbers of possibilities, can any finite size data set be big enough to adequately test your algorithm? And also, as computer vision gets a bit more ambitious, shouldn't we start worrying about the worst case rather than the average case? Our performance at the moment, is generally based on random sampling. So we're calculating, performance is sort of the expected version. But, you don't want a Tesla to detect pedestrians on average. You want it, to the worst case, but never, always to be able to detect pedestrians. And if you're designing computer algorithms on CT scans to find tumors, you don't want it to be on average good at finding tumors. You want it to be really good. You care about the worst case. So here is just a conception here, just to make people think a little. An adversarial examiner, instead of testing an algorithm by its performance in the random samples of images, which is what we do now, allow an examiner to test a sequence of images where each image is selected based on the algorithm's performance on earlier images. So this allows the examiner to probe the weaknesses of the algorithm, let your worst enemy test it, not by a bunch of random samples. Because I think conceptually, would you really, would a professor test his or her students by asking them a random selected set of questions? No, you wouldn't. You'd ask them to a set of questions where each question depended on their answer to earlier questions. Okay, so that's the issue about testing. How should you test? You need to be able to potentially test on an infinite set of images chosen adversarially. Okay, now if your data sets are combinatorially large, then you run into another problem, which is how to train algorithms. And the answer here is, and this will be the last part of the talk, we should train models that are robust to data sets which is related to what's now called out of distribution learning. As parenthetically, I'd say it may be sensible to study how human infants learn perception, because this is very different than how human machines learn it. And the human visual system still remains the gold standard for general purpose vision. So now to move on to a concrete example of this, I'll discuss training algorithms on data sets with limited occlusion and testing them on data sets with occlusion. So humans significantly outperform deep nets if you show them images with heavy occlusion. That's been tested. And can you design algorithms which can do better? So here, and I've left myself only a little time to describe it, but this work is in CVPR 2020, a Kortulewski et al. So there's more information about it there. So again, in natural images, occlusions happen all the time. These occlusions could be considered random attacks here because they're not, at least not in the way we're doing it. We're not trying to target the worst case. We're just putting them on at random, but extending them to attacks is a natural thing to do. The occluders, again, highly variable in terms of shape and texture. So you really have exponential complexity. And vision systems must generalize into these exponential complex domains. Deep networks, you can evaluate them on this. They do not do badly when there's a lot of occlusion. This is from COCO dataset, where you divided it into low occluded, middle occluded, and high occluded. So they don't do very badly on it. And they do, of course, enormously better than anything we had before deep networks, but they're not performing terribly well. You can certainly improve them by training of augmented data, and you get larger amounts. The performance certainly gets higher. On the other hand, as being argued, in principle, the amount of extra data that you'd have to train on might end up by being combinatorially large. So here, think of it from a different perspective. Instead of having a standard deep network that has features and has a top is discriminative, get a model which is generative. So the first part of the deep network is the same, captures features up here, but then at the top, it's got a generative model of the features. And that would be based on an object, the object viewpoint, etc. And then it would be modeling the features, and it would be modeling, and this is important, it would be modeling the spatial patterns. There's a little bit of mathematics here, but I'm putting it up more or less just to show that there is a little bit of mathematics, and that the model here is generative on these features, conditioned on the object, conditioned on the model. So here is perhaps a nicer figure. At the top, class schools would be objects. Then there would be class mixtures, which would correspond to viewpoints. Then there would be feature vectors here, which we used to call visual concepts, which are roughly like part detectors. This model, I should say, is trained in an end-to-end manner. It's not given any supervision about the mixtures or anything like that. So it's given exactly the same information that the deep network has, but the algorithms for learning enable it to estimate these mixtures and so on, these parts, etc., in an unsupervised manner. A little bit of details, math details there, so we'll skim over it. Here is a global overall loss function. You can minimize this. Part of it can be minimized by standard backpropagation. Other parts would be minimized by clustering, because you'll need clustering and so on to get the internal mixtures. Okay. These parts here are going to correspond to parts, roughly. This hasn't been fully quantified, but they would correspond to, here is an engine of an airplane, here are windows, here are the front wheel of a bike. And so the idea is that the models would learn so that for a particular viewpoint, they would expect to find a particular part there in that position. Okay. The mixtures here Here are bicycles from the side, bicycles with 3 wheels, etc., bikes from different angles. Again, learned unsupervised, not learned directly. And for the occlusion model, now that you've set it up as a generative model, the occlusion is almost trivial. Because the generative model is going to say that for any viewpoint, any object, any viewpoint, you have a distribution of the feature vectors at particular places on the object. Okay, you're going to have features for tires in the front right of the car, if you see it from the side, features for windows in other parts of the car. Okay, so you can predict what feature vectors you are going to have if the car is there from that viewpoint, or the bicycle, or whatever you're looking at. Now, if you find that some of those features are there in the right positions and a few are not, you then decide that the few are not are probably occluders. So what you do is you extend your generative model so it's not just generating the feature vectors, but it allows the possibility that the feature vectors at a particular position are generated by a random process that generates something which is not on the object. Okay, so here is mathematics of that, fairly simple. You know, so it generates something of what the object does not look like, so you can just get that by taking a random set of images. Okay, then, so now generative model allowing certain features to a particular position, you know, at different positions to be generated by some other process. So if you've got an image like this of the car, the algorithm is able to first say that it's a car, say the viewpoint of it, but is also able to say that this tree here where my mouse is moving, well, that's not the features it expects to find from a car seen from the side. So it decides that they're occluders. They're generated by this alternative occluder model. Similar for this vertical bar here. This is not what the model expects. So it switches over and says the occluder should explain it. And then this model of the image of the face of the human again. So the generative model generates the features. You're explaining why certain features are missing because of occluders, which means that as well as having some robustness to occluders, you've also got the ability to localize them to find where the outlier model switches on. There's a competition between the object model that's generating the features and the occluder model. Here called the outlier model. So here's quantitative evaluation of it. You can do this, you can put that in, and then you can sort of get graphs and numbers like that, which are all nice. But so far, I think I've given you the main idea. Okay, now you can then see how well do we classify these vehicles. It's only working here on vehicles, has been extended to other models since then. And so here, VGG, ResNet, results are not so good. As you put this in here, you use these comp nets, which are generative on the feature vectors. You do a lot better and you get a far higher result, even under fairly occluded positions, fairly occluded objects, as well as being able to estimate them. They can be applied also to object detection. There's another thing about that, and there's some interesting aspects of that. But again, the idea is you're generating it. You want to be robust to occluders. You want to be robust to context. Okay, so that's a rather fast overview of the technical work. But here is the conclusion. First, that adversarial attacks, I think, are not just sort of fringe interest. They're critical for dealing with the infinite space and the combinatorial complexity of real-world images. The space of images is infinite. You know, the number of metaphors, they're islands in the vast infinite dimensional sea. There are also different image domains, analogous to different tribes with different languages, and domain transfer is critical, as well as dealing with perturbative adversaries. Then the space of images is combinatorially large. If you think of how images are generated from computer graphics, no realistic data set can capture this complexity. Maybe we need to rethink the standard paradigm for testing it, possibly look towards adversarial examiners that try and target weaknesses rather than random samples. And finally, perhaps we need to develop new algorithms. And I've shown you one example, CompNets, which can be trained on one data set but can generalize to another. And I think we'll also have other talks about that later. So that's the end of the talk, and I'll stop now. So thank you very much for your attention.
Hey, Alice, thanks for your talk. Yeah.
Okay, I'll mute myself now.
Okay. Xin, you can. Yeah.
Yeah, then when our next speaker is setting up, then I will introduce our next speaker, Professor Alexander Madry. So Alexander Madry is an associate professor in the ECS department at MIT. His research centers on arithmetic graph theory and understanding uncertainty in the context of optimization. Alexander received his PhD from MIT in 2011. His work has been recognized with a number of awards, including a Sloan Research Fellowship, a number of Best Paper Awards at Fox, Soda, and Stock conferences. Welcome him.
Okay, thank you. Can you hear me?
Yeah.
And can you see my slides? Great. Okay, let's get started. So yeah, welcome everyone, and thank you for the invitation. So yeah, what I wanted to do today is talk about some of our group inquiries into trying to understand what do our models learn, and is it the right way to learn, or maybe not the perfect way to learn. So let's get to it. So the point of start here is our well-known current machine learning research pipeline. Okay, so the way things happen usually is that there is a data set that we know and love, like ImageNet, and then well, we train a model on this. And of course, the way we know whether the model is good or bad, well, there is some test set that was held out and unseen that we test the performance of the model on, and kind of the corresponding, this gives rise to a benchmark that kind of in which we want to evaluate how good, how well our model is working. Okay, of course, this is not a one-shot process. So essentially, whenever we train a model and we see how well it does, well, we learn something from this. And then we try to, tinker with our model to get the performance better and better. And kind of this cycle of improvement leads to, better and better performance on our on our benchmarks. Okay, so this is kind of how, from a bird's eye view, our research, the research in machine learning can be viewed as. And of course, there's a bunch of things that, when we look at this and we work on this, we should and are concerned about, okay? So one of the most obvious things that we worry about is this, I would say, classic overfitting, okay? So essentially the thing is that, well, I train my model on this, data set, on the training set of my data set, which I can do whatever I want on. And then I would like the performance on this training set to extend to this unseen test set. Okay, so this is the whole question of, okay, are we maybe memorizing the training data, or are we learning it in a non-generalized manner? And this is what classic machine learning was focused on and made many advances, to try to counteract this possible worry. Okay, so that's one concern, but not the only one. So the other one that kind of came to realization a bit more recently because of actually all the progress, and it's a bit more subtle, is this question of adaptive overfitting. Okay, the question is that actually, this, deployment of a model is never a one-shot process. We always, when we see the performance of our model on this test set, we kind of use this information to try to improve how the model does. And kind of, as a result, technically this test set, since it's a fixed test set, it no longer is unseen. And over time, you will be worried that maybe we are doing an analog of p-hacking here, that kind of we figure out, we tune our framework to do well on this particular test. Okay, and that's what adaptive overfitting is about. And people worry about this too. And we will talk about it later a little bit more. But what I want to talk today is yet another concern that actually maybe people don't seem to think that much about, although I would lie if they said people don't think about it at all. And essentially what it has to do is, well, it is based on this realization that, as much as we like to focus on this data set model accuracy kind of triangle, there is one other big element that is part of the system, namely whenever we create a data set, it's always to view it as an abstraction or a kind of a way to capture some actual real world task. So for ImageNet, you could view it as an object recognition in the wild, as essentially like the real world task that you really would like to solve. And ImageNet is just a way for you to try to train models that solve this real world task properly. And essentially, once you realize that there is this kind of additional element, and actually you in the end you care really about this element to perform to be solved well, then essentially you start to asking yourself, okay, so as much as we can make sure that this triangle of dataset models and test accuracy kind of works the right way, how do we know that maybe we are overfitting to this whole benchmark? Essentially, instead of trying to make progress on the original real-world task, we end up making progress just on this triangle, kind of this evaluation, like this way we evaluate the model and the way we kind of this proxy version of the task we really care about. Okay, and that's something I want to focus on today. And kind of so the question is, how well do our data sets reflect the real world? In particular, what dataset biases do models pick up? And how are these biases introduced? Like by bias here, I mean kind of what kind of things to learn that are in the dataset are actually not generalizing to the real world task that the given dataset was supposed to model. Okay, so let's dig in. So the point of start here is probably like the simplest setting, the simplest type of bias you could think about in the context of computer vision, namely background bias. Okay, so essentially how much backgrounds are incorporated into the decision process of the state-of-the-art model. So essentially, like, well, the first question you would ask yourself, okay, so is there even a signal in backgrounds? And you can just run simple experiments, and it's easy to see that the answer is yes. That it's not only that there is signal, but our models can definitely extract it if asked to. But of course, this alone will not be too shocking, because also humans can use backgrounds, and actually there definitely is signal in the background. Like sometimes it's easier for you to recognize a person if this person appears in the right context. So essentially, if my work colleagues appears like I see him or her at the vacations, like in some resort, it might take me a moment to realize who that is. So this is definitely not surprising by itself. And what we really wanted to do, and that's essentially what our recent work with my students was about, is trying to get a bit more fine-grained understanding of what exact nature of this dependency is. Okay, so to this end, what we did, we essentially create various versions of like mixes of like when you kind of like data set, like versions of the original data set in which you only keep the foreground picture, foreground object, or you keep a foreground object and kind of overlay it on top of different backgrounds, either coming from some other image from the same class or maybe image from a different class, or sometimes you just show backgrounds alone. Essentially, we have this like different data sets to kind of try to pinpoint exactly like what from the background are our models using and leveraging, if at all. Okay, so I will not be able to give you like a full overview of what we found, but like the one general finding is that in general, kind of model accuracy is significantly reduced when kind of the background signal is not kind of like is not fully in sync with the foreground object. And some of this is of course part of just the artifacts of our way of combining the backgrounds, but it turns out that there is more to it than that. But one finding that I wanted to bring your attention to is so-called adversarial backgrounds. So it's not only that the models do depend on backgrounds, in the classification, which again is not surprising by itself. It turns out in some ways you could claim they are overlying on it. Essentially, like what is possible is that for a vast majority of images, you can fool the model to think that the classification of the image is of the foreground object is different to what it should be by just choosing an adversarial background for it. And in fact, there are some backgrounds, and here are some examples that like they work for a large fraction of images to essentially to like for a large fraction of foreground objects to fool the model into believing that the class that is correct for this image is the background class as opposed to the foreground class. Okay, so this is kind of a worrying. Again, it's okay to to rely on backgrounds to get a better better classification, but if it's so misleading that it can completely like make us not pay attention to the foreground image, foreground object, there is something to be fixed there. And this is kind of the next question that we kind of ask here is kind of like, can you get more background robust models? And it turns out that the answer is yes. One natural way to do it is just to randomize the backgrounds during training. And it does help, but also it decreases the base accuracy, because essentially, like, well, the signal of the background that was useful for classification before is no longer there. So somehow you can't really, get the top performance anymore when you do that. And the other thing we looked at is essentially we looked at the progression on, like, as we improve our models in terms of, like, let's say, image net accuracy. So we looked at, like, different, like, state-of-the-art models at different points of time, and we wanted to understand, how this reliance on backgrounds, in particular vulnerability to adversarial backgrounds, how does it change over time? And the good news is that in general, like, as our models get more accurate, they also become more background robust. Although interestingly, it doesn't mean that they don't rely on backgrounds. They do rely on backgrounds, but they are less likely to be fooled by the adversarial background. So essentially, like, things are going exactly the right way we would expect. Okay, so this was just just a simple example of, like, how to study particular biases that come from the way our data sets are created. Like, as a human, you know that it's all about the foreground object, and the background could help you, but if you know what the foreground object is alone, you should not be using backgrounds. For the model, this is completely unclear, and that was the evidence we have seen. But this was just an example of a bias, and by far it is not the only one. So what are maybe some more subtle kind of biases that come into our model, in our data sets, and also where do they come from? Okay, so essentially, like, so let's just start. So what kind of biases could be there? So what we have over here is just 3 examples of ImageNet inputs. And here are, like, ImageNet classes that, actually correspond to these images. Or do they? So actually, I lied to you a bit. So actually, these classes I provided here, they actually are not the correct ImageNet labels. The correct ImageNet labels are the ones in red. And you might say, well, like, essentially, like, you can ask, okay, so yeah, we were wrong. We are not good at ImageNet yet, and maybe our knowledge of dog breeds, it still needs kind of improvement. But the other reaction, if you kind of look at what's happening here, you might see, okay, but, like, where this answer is really wrong, like, is it really so obvious that this is a church, like the picture on the left is a church and not a monastery? Not really. So there is something going on here, that kind of these labelings might be kind of have some biases and kind of counterintuitive leanings towards, like, one class versus the other. And kind of we wanted to like, kind of dig a bit deeper into trying to understand what might be the problem here and how much of a problem is that. Okay, so to kind of understand even, like, why these biases might be happening and why we might want to ask these kind of questions, well, we should think a little bit about how our data sets are created. And yes, usually when you think about, like, how our data sets are created, you kind of have this image in mind that, okay, there's a large collection of real world images, and then you just pass it to some expert annotators that figure out the perfect class for each of these images, and kind of that's how the ground truth label is created. So this is kind of the idealized view that we actually would like to believe this is the case. But if you think about it for a moment, you realize that this kind of approach just does not scale to millions of images like ImageNet and thousands of classes like ImageNet. Okay, so this will just not work. So what do people actually do in practice? Well, like, one of the popular approaches in practice just works as follows. In particular, this is the way the ImageNet and some other large-scale vision model datasets are created. So you kind of first figure out what will be the kind of structure of classes that you want to even have, and maybe you use WordNet as a seed here. And then what you do is essentially, like, for every class that you want to have, you just, like, use search engines like Flickr or, like, Google image search to find essentially, like, you plug in this class name or its variations, and you look at all the images that you will get back from this. And then, of course, like, you expect that most of the images are indeed examples of this class, but you want to have some validation, and you kind of run this crowdsourced validation, which essentially, in the context, for instance, of ImageNet, boils down to essentially showing the image to a human and asking, does this image contain an object of class X, where class X is the candidate label that corresponded to, like, the search term that you entered where you retrieve this image. Okay, so this is a nice way to do it, and actually definitely scales much more nicely than the idealized approach. But as much as it works and it gives us very interesting and useful models, it has kind of a problem. And the problem is that, like, essentially, if you think about it, like for every fixed image, we always have a candidate label, and all we are asking the human validator is this a possible label for the given image? And we ask them this just for this only one single candidate image, a candidate label, and also we ask it in isolation. So the annotator might not even be aware that there could be other possibilities for the class. So this is a very leading question like that. So this is kind of the problem. And in particular, you can see now why the images that I showed you before might kind of got these different labels, just because the seeds, like the image was retrieved for the query church as opposed to monastery, and then to humans, either one would work. So they kind of validated the one that was given to them. So, so okay, clearly something can go wrong, but of course the question, and this is the, kind of the motivating question for our recent work, is to try to understand, how much of the problem this really is in ImageNet. Okay, so to what extent this kind of biases coming from this validation process actually could, distort, the kind of the biases and the performance metrics that we currently use, for instance, to evaluate ImageNet. Okay. So of course, to be able to, to answer these kind of questions, well, we need to first have some detailed annotation. Like we need to have some better notion of ground truth to compare it against, what is currently in ImageNet, and that's what we want. That's what we embark on first. And of course, ideally, what you would like to do, you would like to just show, example ImageNet images to people and ask them, okay, now classify, each object in the image. So first of all, you actually recognize the possibility that there might be more than one object in the image, and then you can ask them, classify, each of these objects by, like assigning it to one of the 1,000 possible classes. So that's what we would like to get. This way we would get this like more fine-grained, more dense annotations for our images. But of course, again, this is not feasible. Like we can't people to, realistically be able to navigate 1,000 classes to begin with. So what we did instead is kind of the following simple, but actually surprisingly useful idea is what we did is kind of try to kind of pull top 5 predictions from a variety of different models just to kind of get a diverse set of proposals. And essentially based on that, we got a narrowed down set of even possible classes to consider for a given image. So instead of having, confronting the annotators with 1,000 classes, in the end, they end up being confronted with 8 possible classes, like for any of the objects that might be appearing in the image. Okay, and so the kind of task that they are asked then for is just the following. So okay, here are some, let's say in this picture are 3 possible classes that may be relevant for this image, and they just essentially have to say which one are valid and also which one is the main object according to them in this image. Okay, and the important thing is that they have they are explicitly made aware that there can be multiple labels that are valid, and they have to really think about this question of the main object as well. So this is the kind of questions we ask. Then we aggregate this over worker, and essentially like what we get out of this is this kind of nice annotations of like for an image, like what are all the objects in there, like how many objects is there, what kind of labels are valid for each of this object, and also what is the main object as viewed by annotators here. Okay, and this is exactly the kind of information that you would need. And kind of like, we really like this procedure because you can view it as a like bootstrapping the ImageNet annotations. Like in some ways, now that we have this initial labels in the ImageNet, and then we train model based on them, actually like, we can view it as some way of aggregating all of this insight that were kind of, provided by this collection of images plus labels. And now we are kind of doing the second run step using annotators again to just like refine and kind of sharpen these predictions and make them more fine-grained. So I think this is kind of, this procedure could be used for other data sets as well and for other purposes as well. Okay, this is what we did. Now the question is, as long as we have these annotations and we did it just for 1/5 of all of the validation set of ImageNet, we can now ask questions. Okay, how accurate ImageNet labels actually are once as confronted against this ground truth. And there's a bunch of findings, and again, you need to look into the paper to see all of them, but I just want to bring attention to some of them. So one of them is that indeed this multi-object images is not something that just happens to happen from time to time in the ImageNet. Actually, like 1/5 of the images we labeled, and they were like random images from the test set, contain more than more than one label. Okay, so it's like this multi-object, multi-object nature of, of this, of these images is actually something like that applies to a large fraction of the test set. Okay, so this is just an example. This is almost honestly an extreme example where there is like multiple valid objects. But again, like just if you ask for 2 objects, there's plenty of images like that. And now what happens is, okay, you can just wonder, like, if there are like at least two possible correct answer for an image, then like, how does it, how does it kind of relate to the top 1 accuracy? So that's what we wanted to do. So essentially what we plotted is just, we looked at the, accuracy on the full test set, which is kind of our current measure of quality of a model. And we confronted it against the, accuracy on the subpopulation of, images that are single object versus images that are 2 or more objects. And what we got is kind of the plot on the right. And essentially like this plot, in both cases, we see improvement over time. So better models are doing better on both of the subpopulations, but you see that there is like a large performance drop, like 10% performance drop between the performance on the multi-label images versus the single labeled images. Okay, and now you might say that maybe just these images are hard, but this turns out to be that actually that's not the case. So essentially, like if we now count a prediction for this multi-object images as a correct if it matches any of the objects according to our annotators that is present in the image, then essentially we are getting this curve over here, which essentially shows that this drop in performance essentially disappears. So essentially like the major driver of like performance loss on this kind of images was just this fact that they were ambiguous, inherently ambiguous. Okay, so that's interesting. And of course, again, but now we can dig a bit deeper. So once you know that the objects, that the images can have more than 1 object, you can ask yourself, okay, so which, like if there's many objects, maybe like which object does the ImageNet label correspond to? And your hope would be that like most of the time, or always, it would be the object that is kind of main in the image. This actually turns out not to be the case. So essentially, like often the image that is viewed as the main, like the main in the image by an annotator is not the one that the ImageNet label corresponds to. So it's essentially like in general, this like ImageNet labels tend to focus on like very specific kind of very distinctive object in the image. So here are just examples. So in the middle example, kind of, even though obviously probably our instinct would be that this is about a suit, to an ImageNet model, like they like the fact that this is a bow tie, and probably this is just a bias coming from the way the search engines, search engines work, where kind of this is something that probably you would get if you enter the bow tie into the picture. Okay, but kind of the labels a priori do not try to be as general as possible. They just like whatever works as long as it's a valid labeling. This is it. So actually, like there is a problem that the main object is often not the ImageNet label. So that's really a problem. But what is interesting is that actually models kind of seem to be aware of that. And they seem to pick up on these dataset biases. And they actually realize that like on this middle image, you actually should be talking about the bow tie as opposed to a suit. So kind of, in some ways, instead of like having like 50-50 chance of getting the right class, they actually do realize what ImageNet is really means in this image, and kind of they are extracting these biases there, even though no, this is clearly not what we would intend to have. Okay, so this is kind of one type of insight. The other type of insight you may ask about is saying, okay, so now that we have this like more fine-grained annotations, we can ask ourselves, okay, so how good ImageNet models really are? Okay, once we take into account all these issues with labeling, and you can just do this kind of human-based evaluation in which you look at the prediction of a given model on a given image, and instead of saying it's right and wrong or wrong by just confronting it with the ImageNet label, you can actually ask humans, okay, is this classification actually a valid classification for this image? Okay, and what do we find? And what we find is like from this point of view of metric, again, as we improve, over time on our like ImageNet benchmark, the models improve on this metric as well. But essentially what is interesting is that somehow, in some ways we seem to be hitting this non-expert annotated baseline. Like in some ways, currently, if you look at the incorrect predictions of models and ask the humans how incorrect they are, they honestly often are not able to take to tell the difference between this incorrect prediction versus the correct ImageNet label. So in some ways, kind of our models might be already getting to this baseline, which probably is the best we can hope for, currently, and pushing them to get even better accuracy than that might actually lead them to have to force them to overfit to the biases of the dataset, as opposed to getting better at the task that you want them to be good at. Okay, so that's kind of a very interesting, very interesting thing that we realized, and kind of, it shows that we should be careful, as we try to push the percentage on the, ImageNet accuracy further and further. We should be really careful if we are not asking for too much, and as a result, we will distort the, the progress that we are making. So this is kind of what I wanted to say about this benchmark versus dataset alignment. But I just wanted to come back quickly to this adaptive overfitting because it fits the story of biases in a nice complementary way. So essentially, as you remember, kind of the adaptive overfitting was all about this kind of avoiding p-hacking. So essentially saying, okay, if we have a bunch of different researchers and different models that evaluate themselves on the same test set, maybe we end up, not making as much progress as we think we are, because we are essentially overfitting to this particular test. So one way to measure it is kind of this idea of dataset replication. And the idea here is exactly to say, okay, so if we are worried that we are overfitting to this particular test set, how about we create a new independent, a new test set that is trying to match closely the underlying distribution, but be different to the test set that everyone kind of compares themselves to, and see how the performance on the original test set transfer over to this new test set. Okay, so this is kind of this really neat idea of how to try to diagnose this problem. And indeed, in particular, Rect and all were pioneered this by kind of looking at the ImageNet dataset. So they create this ImageNet v2 dataset. So yeah, so they started from the ImageNet, and kind of what they wanted to do is they wanted to source new Flickr images, because Flickr is largely where ImageNet images are coming from. And they kind of course, they can't just take a random subset of of Flickr images, because the Flickr images that made into ImageNet were selected for quality in some way, and essentially the kind of the way they were selected for quality corresponded to a metric called selection frequency. And what they wanted to do, they wanted to get a new subset of Flickr images that control for the selection frequency as well. Selection frequency is just roughly the question is that if I show an image and I ask you, is it an image from this class? How often will an annotator say yes versus no? And kind of course, so what you would hope is that, the better selection frequency, you actually have a better quality image. The lower selection frequency, this is a lower quality image. And what you would like to do is you would like to make sure that, you have some threshold, and kind of the images you take are the ones that are in general have a large selection frequency. Okay, so that's kind of the intuition. And what they did is kind of they set up a pipeline that essentially tries to match the selection, measure selection frequencies both for the the sourced Flickr images and for the original test set, and they have to remeasure it because we don't have access to the selection frequencies that were used at the time when the ImageNet was created. And what they do is that they essentially just match the empirical selection frequencies they find to kind of make sure that this new test set has the same distribution as the old test set. Okay, so that's what they did, and that's how they got the new test set. And essentially now, what were the results that they got? Well, essentially they get two kinds of findings. So the first kind of finding was that actually they did not find evidence for adaptive overfitting. So that's a good news. But what they also found that there is a significant accuracy drop in the performance on the new test set as compared to the original test. So this is bad because it suggests that our models are kind of brittle to this kind of distribution shift that underlines this problem. And and now it's natural to ask, okay, so but where is this? Why is this new data set harder though? What makes it why our models that worked well on tests on the original test set seem to perform so much worse on the new test set? And that's something that kind of we wanted to take a look into a bit more, because it's important to understand where this kind of accuracy drop is coming from. And what we discovered that actually one possible explanation of at least a large fraction of this, of this drop might come from a statistical bias, a subtle statistical bias that actually this creation of this new test set actually entailed. And essentially, if you remember, all that the new test set was trying to aim, it was trying to match the selection frequency distribution of the original test set. But the problem was that selection frequency is just an idealized thing. This is just something that we think about, if we had infinite number of annotators trying to and we would ask each one of them about this question, And of course, in reality, we cannot afford to ask infinite number of annotators. We only ask a finite number of them, and usually a small number of them. And as a result, this reading of selection frequency ends up being noisy. And of course, for a given image, this reading is actually an unbiased estimator, which is fine. But it turns out that the way we do the matching actually leads to a systematic bias that is kind of not unbiased anymore. And essentially, like as a result, what we show is that it makes the images that end up in this new test set to be actually of big harder than the ones that were in the original test. And essentially, like how can you now try to validate this hypothesis? Well, one way what we did is just we essentially used statistical modeling to try to correct for this bias. And I will not get into details of how we do it, but the point is that once we kind of do that, then essentially like this drop reduces significantly. It goes down from like 11.7 to 3.6%. So it's still there. So there's still something to understand, but at least it's like significantly reduced. And we get similar results also with with other techniques. Okay, so that's all I wanted to say. So let me just conclude and just say a few words towards the end. So first of all, I think the message that I want you to have is that like what models do and do not learn is not always clear, and we really should be careful about studying it if we think about trying to drive our field by pursuing benchmarks, in particular if we think about robustness. And essentially, like the models are affected by both the biases in the world, but also biases over dataset pipeline. But we can improve the situation if we kind of recognize these biases and we account for them. So going forward, the question is, what other biases do our models learn from the data? How do we train the models so they avoid learning or relying too much on these biases? And essentially, like, how do we measure performance on the underlying task we care about, meaning it's like real world object recognition, if we always need to, in the end, project it down on some particular benchmark? So thank you. And and I think I will not be answering questions now, but there will be a session where I will be answering questions.
Yeah, so thanks a lot for your presentation.
Yes, so I will just stop sharing.
Yeah, thanks. So Jelen, could you can share your screen now, and also you can unmute yourself.
Can you hear me?
Yeah, cool. Then yeah, I will introduce you first, and then you can go ahead and have your presentation. So Professor Jelen Fernandez is an assistant professor at the University of Wisconsin-Madison in the CSD department. His goal is to enable society to gain the benefits of emerging technologies without the security and privacy risks. Professor Jelen Fernandez has received 2 Best Paper Awards at IEEE SMP and IEEE Secure Development for his work in smart home security. He will give his talk today about physical attacks on object detectors. And let's welcome him.
Well, thank you. Thank you for the introduction. Thank you for the opportunity to speak today. I appreciate it a lot. And I also appreciate the effort that goes into organizing these virtual events at a time like this. So yeah, I'm a professor in the CS department at Wisconsin-Madison. I do research in system security, kind of broadly defined, and one of my focus areas nowadays is cyber physical systems. So, unlike many of the speakers, at this conference, this workshop, I'm not a computer vision or even a machine learning researcher. And so, much of the things I'm going to say today kind of come from kind of a computer security perspective and how, some parts of the computer security community view some of these adversarial example problems. Okay, so, as we all know now, these adversarial examples are a major research area, a lot of papers being written, and early adversarial examples kind of introduce this notion of digital attacks, right? So the attack is going to basically digitally add and subtract pixel values to an image, and then these changes are going to be so small that a human is not going to be able to see it. And then what you end up with is, for example, in this classification task, this dog may look like something that is not a dog to the classifier, right? More recent work kind of introduced the notion of physical adversarial examples. And a lot of this early work was kind of done in the context of classifiers. And so here I'm showing you an example of our prior work that appeared at CVPR
some years ago. And here the idea is that the attacker can somehow manipulate a physical object. In this case, in our case, we were interested in stickers on stop signs. And the result is that once you run an algorithm to compute these kinds of adversarial examples, you can modify a physical object, and then you can take an image of that object, and then that resulting image will be misclassified. Now, of course, our work was not the only in that space. At around that time of that work, there was a lot of concurrent efforts, and we have seen many examples. For example, people can wear different kinds of eyeglasses. You can print things on papers that can hijack the attention of these classifiers, and so on and so forth. And the common kind of thread in all of this work was that it focused on classifier networks, right? And so that is all well and good, but a more fundamental question kind of coming from the computer security world is that, why should we care about these kinds of attacks? And more specifically, why should we care about these physical attacks, right? Well, should we care about them at all? And one of the driving questions in our work, and I presume in a lot of the concurrent work at the time, is that we are seeing many of these machine learning models being used in the cyber physical systems like cars and voice assistants and drones and stuff like that. And we find that they're being used in pretty critical aspects, right? So I mean, you can see that in the cars, for example, they use it in perception and sensing, and sometimes even control. And so naturally, the implication is that if somehow these adversarial examples are physical and they can cause behavioral changes in these physical systems, then that would be very bad for their safety and security. Okay, but that's not the complete answer why we should care about these physical attacks. The second part to that is kind of the threat model, right? So as I mentioned, a lot of the early work had this digital threat model where you would manipulate the pixels of a file that goes into the machine learning model. But again, if you take this in the context of cyber physical systems, this kind of threat model is not the most reasonable, because if you assume that an attacker somehow can digitally manipulate the pixels of an input vector going into a model running on a vehicle, they have already won. Right? They've already won the game. We don't need to, there are easier ways to carry out the attack. They have digital access to the computer systems on these things. And so, the second part to answering this question is we should be concerned about this is that only if these adversarial examples will have macro level effects. Okay, and I put a double star here because, from a cyber physical systems perspective, machine learning is not the first vulnerability we have ever thought about for these systems. In the computer security world and the CPS world, we have many other kinds of vulnerabilities that do have end-to-end effects that we have looked at before. But the new thing is that, if these machine learning attacks can have an end-to-end effect, then it becomes yet another attack vector that we have to take into account in our threat model as defenders when we are trying to design robust physical systems. So all of the work in understanding these physical attacks, I view it as kind of taking a first step towards this larger question of whether we should care about these adversarial example or physical machine learning attacks at all. And so, my talk today is kind of going to be in three parts. First, I will discuss some early work we did some years ago that kind of takes another step in this direction of answering whether we should care about physical adversarial examples. And so, I'll talk about this paper we published at Boot. So, for those of you not from the security community, this is the Usenix workshop on offensive technologies Boot. It is a place that is exclusively publishing attacks on various kinds of cool attacks on systems. So I highly encourage you to check that out if you're interested in what's going on. Then I will briefly review some concurrent efforts that attack these object detectors in various ways. And finally, I will take one step back and try to again contextualize all of this work to show you where we are and where we must go, kind of again in service of answering this larger question of whether we should care about these kinds of attacks or not. Okay, so, we have seen this work in the context of classification. Now, in the deep learning world, in computer vision world, we have many kinds of tasks. Object detection answers the question where the objects are in the scene and what are they as well. So it's like classify, detect and classify. And one step further is semantic segmentation, where almost every pixel is kind of being labeled as part of some larger concept. For example, building window skies and all of that. The focus of our work was on these object detection models, and that's kind of what I'm going to dive into here. Before I dive into that, I just want to spend a few minutes motivating why object detectors in particular, right? Why am I not focusing on other things? Obviously one reason is that they detect and classify. So in some sense, they are more useful and more general than a classifier. More useful to CPSs is that they work at relatively high frequencies, right? So that is like they can process and give you output at high frames per second. And this is very useful for real-time systems. So all of these cyber physical things are operate in real time, and your machine learning somehow has to be able to operate in that kind of constrained environment. And finally, we are beginning to see some of these object detectors being used in realistic systems. So for example, Apollo Auto is an open source self-driving car software from Baidu. And I will kind of get into some details of this towards the end of the talk. So, unlike classifiers, there are a few kind of specificities in object detectors that make it a little more challenging to attack than the work we did with classifiers. And so here I've kind of listed a few of these examples. The first is that, a detector kind of processes an entire scene. And this kind of implies that they have a lot of contextual information to take into account while they're making that prediction. Second is that, the model is not constrained to, kind of do or die, like give me a label or else, you just die. Here they can produce many objects, many labels, so they're not constrained in that kind of, that setting. Third, and this is kind of the most interesting one, the location of my target object, right? So as an attacker, I have some target object that I want to attack. The location of that target object within the scene can vary widely, right? Unlike in a classifier, which, where the images are relatively tightly cropped to the dominant object, in a detector, these objects can be anywhere. And so, at the time we were doing this work, we had just completed the project on the stop signs and classifiers. And we were curious, whether it is possible to extend that framework that we had built and see if we can make small changes to it and still attack detectors. And that was kind of, one of the questions we were trying to answer. So before I go into how we ended up attacking those systems, the object detectors, I'll give you a bit of a review on the algorithms we use to attack classifiers, because the detector algorithm is a very small variation on the classifier attack algorithm. And so in classic adversarial example style, you want to minimize some kind of distance function between two, say, images here, x plus delta and x. And delta is your kind of attack, your adversarial perturbation, as long as that perturbation causes the classification label to change. And we don't really work with this formulation. We use kind of a relaxed formulation. This is pretty standard, and we use kind of a loss function to kind of approximate the distance between the output of the classifier and the attacker label. Okay, and this is a pretty standard formulation. And one of the big things in these physical attacks, independently of classifiers or detectors, one of the challenges is to make them robust to changing environmental conditions. And so one of the primary ideas in the work was to essentially, when you're training the attack, you want to model ahead of time the effects of the environment on the perturbation delta here, right? And the idea was to basically optimize over a set of images such that in expectation, your adversarial perturbation is going to gain robustness to those chosen features, through those chosen images. And there are multiple ways to kind of sample from this distribution. We ended up doing a combination of taking actual real images in the real world that simulated these environmental conditions, and synthetic transformations as well. And I guess, a point of difference between the ICML work of Atelier et al. is that they used synthetic transformations. So that kind of will give you, a robustness to environmental transformations. And notice that this is a framework, right? I can keep adding different kinds of transformations if I want robustness to those conditions. And that is really the key point that will be useful in attacking detectors that I'll show you in a couple slides. Another thing about these physical attacks is that we can't just add noise everywhere, right? So unlike a digital attack, in the physical world, everywhere literally means everywhere. And so we need to make it a little more well-defined. And so we introduced this notion of a mask. You can think of it as a matrix with ones and zeros, and so we simply do an element-wise product with the attacker's kind of delta, the attacker's noise. And of course, depending on the shape of the masks, you get different kinds of attacks. And I've kind of shown you very simple black and white sticker attack here. Choosing a mask is a bit of a question. I would say it's still an open question. And we basically came up with a very simple hypothesis that we can use an L1. We can do 2 rounds of optimization in L1. L1 is a sparsity norm, and the idea is that if the optimizer will basically favor less pixel changes over many pixel changes, and they will kind of coalesce around important parts of the object. And so we kind of did this process, this multi-round technique, and we kind of produced these stickers here in a manual process, right? So we look, as humans, we look at the output of L1, and then we say, okay, maybe we should put a sticker here or somewhere here. And that's how we construct the mask. This, of course, is an open question. How do I jointly optimize the attack and the mask? Anyway, so at the end of all of this, you run all of this, you kind of get these sticker attacks, and we did a bunch of experiments in the lab and in the physical world, and we find that they work. Okay. So that was the review. Now, it turns out attacking object detectors, at least in the context of these traffic signs, is not very different. As I alluded to earlier, one major change from classifiers is that the target object can appear anywhere in the scene. Right? And so in a sense, you want your adversarial perturbation to be effective at many of these locations within the scene. And so, put another way, you want translational invariance, right? You do not want where the object is to affect kind of the quality of the attack. And so conveniently, this framework, basically will allow us to model this translational invariance as yet another transformation. So essentially what we do is we model a fixed set of positions within the scene for a target object. We move that object between all of these positions, and then we optimize that over those set of generated images. And so the idea is that if you do this enough times in expectation, whatever perturbation you calculate will be invariant to where it is located in the scene. Okay, so that was the first realization when attacking object detectors. The second realization was that the loss function is going to be a bit different. So unlike a classifier, where you have some kind of cross entropy loss, you have a fixed, probability distribution that is being output. The output of an object detector is a little more complicated than that. And so, here what I'm showing you is kind of the YOLO V2 output format and how we adapted the loss function to work there. So at a high level, essentially YOLO divides a scene into S by S cells. In the implementation we experimented with, S was 19, so this would be 19 by 19. Each grid cell is responsible for kind of predicting up to 5 bounding boxes. So this is kind of a parameter of how the network is configured. And each bounding box is technically these two vectors here. One is kind of an objectness vector, which simply says, okay, what is the probability that there is an object in this grid? And of course, where is it? Center and of course width and height. And then there's a full probability distribution that basically says, what this object might be, right? So if you put all of this together, the output of the YOLO model is actually a 19 by 19 by 425 tensor. Okay, so this is very different from your classifier style output, and so your loss function needs some thinking. Right? And so one of the goals in this attack, in this proof of concept, was to simply, make the stop sign disappear, make the target object disappear. Right? And so we designed a loss function to kind of encode that idea. And so essentially the idea, I've shown it to you here. I've taken this from the paper, but kind of the English description is that, at any round of optimization, you look at the output, you find the maximum probability stop sign, right? Out of all the predictions, what's the stop sign? Which object is the stop sign and what's the maximum one? And you minimize that directly. And you keep doing this through several rounds of optimization, and eventually the probability of a stop sign appearing in the scene will be below kind of the notification threshold of YOLO. So I believe YOLO uses a certain threshold, I believe 20% in our implementation. If the probability of an object is above 20%, it is going to show you that information saying that, hey, here is this stop sign. If it is below that, it's going to suppress. Right? And so the goal of the optimization was to essentially always minimize the probability of the stop sign. Okay, and like the classifier work, we did two styles of attack. We did an attack on with a poster, so like the entire object is covered with this big poster, and we did, of course, stickers where we again manually chose a mask. Similar to prior work, we also did this similar kind of evaluation where we record a video of a camera moving towards the stop sign, and then we simply sample video frames and count the number of frames in which the stop sign was not detected. Right? In this paper, we did kind of two styles of attacks. We did white box attack, we did black box attack, and different settings. Okay. Across the board, I mean, I would argue that, for a first attempt at attacking object detectors, the performance was pretty reasonable. For most part, this the stop sign is kind of disappeared from the output of the model. Okay, so here is kind of a quick video of a poster attack on YOLO v2. Clearly, for some reason, it somehow notices the person, but the kind of the very obvious stop sign is not detected. Instead, there's like refrigerator, banana, umbrella, all kinds of strange things. Here is the same attack, but on a real object with stickers on top of it. Now it's looking, it's noticing bottles again instead of the very obvious stop sign. We also tried this kind of this black box transferability. So faster RCNN is another state-of-the-art object detector system. And this is black box in the sense that we just train it on YOLO and just run it on our faster RCNN, see what happens. For most part, it works okay, but we didn't try to do any special kind of transferability enhancing techniques. Another kind of attack we tried during this work was to kind of create objects out of nothing, right? So we want to kind of cause the detector to hallucinate the presence of objects that humans would disregard as meaningless, right? So for example, this thing I've shown you here, if you print this out on a piece of paper, YOLO would recognize it as a stop sign when, to a human being, at least to me, it looks like a heart of some type. There again, you have to kind of think of a specific loss function. So here, because of the way YOLO works, recall that there is this objectness score and then a classification score. We kind of did this optimization that has two components to it. First, we want to get the model to recognize that there is an object in there, right? So I'm setting it to 0.2 or 20%. So this will at least, show up or kind of get YOLO's attention as, hey, there is an object there. This is interesting. We should probably classify it. And then once we hit that threshold, we switch and we start optimizing the presence of a specific class. So in this case, I wanted a stop sign. And so basically we say, okay, now that there is an object, we need to make it look like a stop sign to this model. So this is kind of a creation attack, attacker loss function. So that is the extent of what we did in that paper. At around that time, again, this is an active area, a lot of concurrent work, a lot of follow-up work. There's another attack called Shapeshifter that did similar styles of attacks on faster RCNN. Right? So we did YOLO v2, this paper did faster RCNN, and you kind of have similar results on these detectors. Of course, there is even more recent work. So for example, there's this interesting paper where you can like print a t-shirt with some weird patterns, and then that somehow makes you invisible to face recognition systems. There's also, I think, believe at this CVPR, these universal physical camo attacks, that will make you look like some other kind of class. So there's a lot of interest in this area, a lot of concurrent work, a lot of follow-up work. And now for this final part of the talk, I want to take a step back and kind of contextualize some of the research we have done and some of the research this community is doing and what we have seen so far. And so, recall from the first part, I said that, one reason for caring about physical attacks is that, if they have macro level effects on physical systems, then it'll be a problem. And so let's look at one system. So this is Apollo. It's a self-driving car system. It's open source. And this is kind of their perception pipeline, right? So they have various kinds of sensors. They have cameras, LiDARs, radars, all of that. And then they go through several rounds of processing, right? There is a traffic light detection, object detection, lane flow detection, many, many things. There's all kinds of tracking algorithms, sensor fusion, many things going on. We are right here, right? So we are kind of like what we have shown so far is kind of physical attacks on object detectors, right? So this is one component of the pipeline. We can trick this, but that's where we are. Now, I guess it is obvious, hopefully it's obvious to you here that, we are after end-to-end attacks, right? My claim is that we only care about physical examples in these kinds of systems if there is some kind of end-to-end effect on this entire system. In terms of physical level attacks, this is where we are, Now, of course, I again caveat this with double stars because in recent times, there has been progress. There has been progress in kind of understanding, if we had to take things some more steps further, what that might look like. So there is some work at ICLR that essentially looks at this tracking process that runs Kalman filters to kind of make predictions one time step into the future about various kinds of objects self-driving cars seeing. And what you might do to fool that. Of course, this work is still in the digital space and they use only camera data, but as real systems, they kind of do sensor fusion as well. So it is a step in the right direction. However, we still need to understand whether these attacks really have that end-to-end effect in the physical world. All the work I've shown you so far is kind of on these relatively two-dimensional objects, rigid objects. There's work on attacking different kinds of sensors like LiDAR as well. But again, the same kind of point remains. We still do not have an understanding of, if I want to create an end-to-end effect as an attacker, how am I going to go about doing that? Okay, so I'd like to end with a few points and some open questions that I do not know the answer to, and I'm happy to discuss them further. So the two kind of learnings I take from all this work is that we can attack classifiers and object detectors physically. We still need to understand physical macro level effects. And there is work kind of going in the right direction, kind of going in that direction of understanding, how we might cause these macro level effects with these attacker algorithms. The one big thought I'd like to end is kind of along this theme of threat modeling. So, as computer security researchers, this is a very basic thing we do, often at the start of a project, right? It's a very basic activity, and it's something that really keeps me up whenever I think about autonomous vehicle security. And I'm going to contend that we still don't have a reasonable threat model for end-to-end physical attacks. So, for example, where in the physical world is the attacker? Are they on the side of the road? Are they somewhere above the horizon of the vehicle, above the road? Are they a human being, a pedestrian? Are they another vehicle? If an attacker is modifying some vehicle, will the owner of that vehicle notice? What do they know about the system under attack? Right? So if you're Tesla, you're not going to give out your machine learning models. Maybe you'll give out hard labels. How do we create those physical attacks with different kinds of assumptions about the system under attack? And of course, what can they modify in the physical world without arousing suspicion among many observers? So, with that, I'd like to end. Thank you so much for the attention. As I mentioned in the start, we are a newly formed security group, MAD-S&P. It stands for Madison Security and Privacy. If you're interested in doing this kind of security-oriented work for adversarial examples, we are looking for students. We're looking for postdocs. So thank you again. I'd like to acknowledge my collaborators. A lot of this work was done with a lot of really great people, and thank you for your time.
Yeah, thanks a lot for your great talk.
Okay, so I will mute myself.
Yeah, and we will move on to the next speaker, Professor Matthias Becken. So our next speaker is Professor Matthias Becken. So he's a professor of computational neuroscience at University of Tübingen and the chair of Bernstein Center for Computational Neuroscience, Tübingen. His research lies at the interface between artificial intelligence and neuroscience and focuses on uncovering the representations, algorithms, and neural computational design principles for perceiving neural networks both in the brain and the machines. His talk's title is Testing Generalization. So let's welcome the next speaker. Hi, I think you are unmuting you're muting yourself. Could you unmute yourself?
Okay. Hello? Can you hear me now?
Yeah, we can hear you now. Yeah, great.
Okay. And you can still see my slides?
No, you are not sharing now.
Okay, good. Then let's turn again. All right, sorry for that. Thanks for setting up this nice workshop and for inviting me. So I think adversarial examples are great examples for differences between humans and machines. And my background is half computational neuroscience and half machine learning. And oops, what's that? Okay. And so I think of brains as decision-making machines. And ideally, so our life is full of decisions and we make decisions in the past, we observe data in the past and we generalize from this for the future and learn. And my dream obviously is the question, can we build artificial decision-making machines similar to the brain? And in order to make good decisions, the key feature is to generalize well from past experience. And for generalization, an informal definition of this is like the ability to handle situations or tasks that differ from previously encountered situations. And so as I mentioned, adversarial examples can be seen also as testing generalization, so with small targeted perturbations. And here's an example. So for instance, if we have a photo and we want to make for humans this to look more like a pig, you can, well, some people do this by adding certain features. And here you can see that basically human generalization is based on parts and attributes that together compose to the meaning of the entire image. For machines, this is a bit different. So if you have a neural network, the same image can be with basically imperceptual perturbations turned into a pig, frog, ostrich, or whatever you want. And so these type of changes exhibit a very different way of how machines generalize and what the invariances of the machines are. So how can we teach machines to do what we actually want them to do? And so the standard setting in machine learning is that we have a training and a test set, and that we assume that the distributions during training and testing are the same. And basically cross-validation is the main feature by which we constrain the solutions to avoid overfitting, what Alexander Matry was already mentioning in his talk. And with this technique, if we have a lot of data, we have seen really great progress on the ImageNet benchmark to become better and better on object recognition. And in addition to that, what made me very excited in the beginning about the progress of deep learning is that not only these we make progress on this particular benchmark, but it was also possible to use the features learned on the ImageNet benchmark for other tasks. And so one didn't have to start from scratch again for solving other vision problems, but the features were quite useful for all kinds of tasks, suggesting that this learning of ImageNet features has captured something about the visual world that is generally useful. And as an example for this property, I took the work from Krieger's Cortes lab originally, and from DiCarlo's lab originally, where they showed the correlation between the ImageNet performance and predicting neural performance. And nowadays, there's a whole brain score benchmark where people try to predict neural responses in the brain. And as you can see in the plot in the middle, there's a correlation. The better the neural networks perform on ImageNet, they tend to be better on these predicting neural responses in the brain. And so the transfer learning setting basically is that you first train the neural network to learn these features, and then you, in the extreme case, you just use the features as are, and you train a new readout in your head to read out and on a new task with new data. And this works surprisingly well. So when we did this ourselves on saliency modeling, so on the MIT benchmark, where many people have been trying to predict where people look. So for each image, you have recorded fixations, and the task is to predict the density of these fixations as a function of the image content. And as you can see here, the densities depend quite strongly on the image content. And by using these transfer learning tricks, you can actually, well, it was possible to boost the performance on this task quite dramatically. So the y-axis is measuring information gain in bits. So basically how much information is shared about the location where people look. And on the right-hand side is the gold standard. And the performance increase, for instance, between AlexNet and VGG19 in the beginning directly transferred also into a performance gain in saliency prediction. And this could be used, for instance, for better image cropping. Another example is for marker-free key point estimation. It's very desirable that you only have to label a few frames in order to be able to extract the key points or track the key points in arbitrary movies. And so also there, using pre-trained networks like pre-trained on ImageNet makes it sufficient that you only need 100 frames in order to get very reliable estimates of the key points that you're interested in. And so this can be used and is used now in many, many circumstances. So this is very nice that you can actually even transfer to new tasks where the model features haven't been trained on, suggesting that these features in deep neural networks trained on ImageNet are learning something about the visual world that generalizes beyond the particular task of ImageNet. However, we have to be aware that the type of features that are learned are still very different from what humans learn. And so one should be aware that one shouldn't equate it with object recognition. And so one very nice paper by Alexander Madry showed, for instance, that if you train a neural network with adversarial examples, the features that the network learn generalize also to images that are not adversarial examples, so that are normal images, and achieve good test accuracy by training on these adversarial examples. So meaning that the features that are used to classify adversarial examples are actually part of nature images and can be used for the classification, but they are very different from what humans perceive in these images. And so the overarching question underlying a lot of what we are doing in my lab is to ask, how can we teach machines to do what we actually want them to do? And if you think of learning as a search problem where you have set up a space of all possible decision rules, there's an intended solution in computer vision. This is often very similar to finding like perceptually similar decision making. And the first thing that you do is that you try to achieve a small training error. And in addition, by doing cross-validation, you also want to have a small test error. And this reduces the set of possible decision rules quite strongly, but it doesn't mean that you that all decision rules that have the same small test error are actually equal to the intended solution. And so there are many, many examples for this. Adversarial examples obviously are a very striking difference between human perception and machine perception, but also there are examples with domain shifts that when noise sensitivity for images, for machines is often much stronger and different from humans. Machines tend to look more at texture than at shape, or are very sensitive to background information, more sensitive to background information, and so on. So I will focus here on two examples. So when about 5 years ago, when we developed a texture synthesis algorithm, we fed the neural network with texturized versions of an image and figured that the typical convolutional neural networks show almost the same logits to the different class labels as for the original image, which motivated us later to make this hypothesis that the neural networks are mostly looking at texture more precise by using a constrained architecture such that the highest layers are still looking only at very small patches, and the classification is done only by summing over all the classifications of these individual patches. So it's basically a bag of feature architecture, which you can think of. You decompose your image into all the image patches that it contains. For each image patch, you make a classification and you average over these classifications in order to obtain the final decision. And with this architecture, you can actually achieve quite good performance already with a patch size of 32 by 32 image patches. And that means since the summing over the different classifiers doesn't depend on the ordering of the patches, that the information that you're actually using is only the texture information and not the configuration of these different patches. And it also allows you to look at those patches that are most decisive for the decision, so that have the strongest impact on the classifier. And so and often this makes sense. So it shows very crucial features or very special features of the different classes. But sometimes also, like for the tench class here, it's rather the fingers of the proud fisher than the fish itself that is most informative or most decisive for the tench class. And another work that shows this difference between humans and machines in the classification is using a style transfer mechanism in order to introduce Q conflicts in the images. So we basically combined texture information of, say, an elephant texture here and the shape information of a cat. And and then you can ask whether the classifier rather relies on the shape information or on the texture information. And in order to make this also more feasible for humans, this decision
What happened?
Hello, I think I dropped out. Can you hear me again?
Yeah, we can hear you now. Could you share your screen again?
Sure. So right. How long did I have been cutting out? So did you see that slide before?
I guess we see the top part of the slides, then you are kind of cut.
Okay. And go on. So it turns out that humans classify these Q conflict images almost always based on the shape information. So this diagram, basically if the dot is on the left-hand side, it means that the decision that the humans made was rather using the shape Q, and if it's on the right-hand side, then it's using the texture Q, and the different dots correspond to the 16 different classes. And if you look at architectures like AlexNet, GoogleNet, VGG16, they're all biased towards using the texture information. And so that means even though you achieve high performance on the test set, the solution that is used for this decision-making is quite different from the decision-making rule that humans are using. So to further constrain the possible solutions, one can apply also out-of-domain testing. And so again, a nice demonstration for this difference is if you impose additive noise during training and say you use white Gaussian noise and you test on white Gaussian noise, then you get superhuman performance, and same with salt and pepper noise. But when you change during test time, the type of noise, even though it looks perceptually quite similar for humans, it can completely deteriorate the performance of the classifier. And so we, again, made a psychophysical experiment with humans, testing the noise robustness as a function of the noise variance, and compared that to these classical architectures that haven't been trained with noise. And you can see that they are much less robust. And then we went on and trained the classifiers with all kinds of different noise and tested whether how well the training with one type of noise generalized to a different type of noise. And there turned out that this generalization didn't work so well in the beginning. And since this noise can be seen also as a domain shift that changes the style of the image, we thought maybe we can use the style transfer method to introduce very different appearances of the image while preserving the content. So as you can do with this method, where the same scene can have very different styles. And so we generated a new data set of the ImageNet where all the images were transformed into different styles, and used this as a data augmentation approach in order to make the classifier invariant against these style changes. And by doing that, turned out that one can still achieve very high performance on ImageNet. And we can then test the performance also of the BACnet, for instance, that I've been introducing earlier. And there you can see that the performance drops much faster than on the clean ImageNet dataset. So for this stylized ImageNet, it's not possible to classify the images based on the texture anymore, but you really have to use the shape information in the images. And interestingly, also the invariance against these different styles makes the neural network much more biased towards shape. So if you look at this diagram that I showed you earlier, what type of cues the network is using. If you present Q conflict images, then it's much more biased now towards shape than to texture. And if you apply uniform additive noise, so that you haven't used during training, the decay of performance looks much more similar to that of humans. So this is this yellow brownish curve. Okay, so one idea to get closer to the intended solutions is that one applies more and more out-of-domain testing. And in this way, maybe at some point arrive at the intended solution. But a very hard test, probably the hardest test, is to use counterfactual testing. And so by making neural networks robust against adversarial attacks, this would be a very hard test to have a similar decision rule as for humans. And for very simple data sets like MNIST, using generative models actually yields or can yield adversarial examples that look quite interpretable to humans. So we designed an analysis by synthesis model where for the 10 different classes, the classification is based on, you could say, 10 different experts that try to explain the current image by generating an image that is as similar as possible to the presented image. And then the expert with the highest likelihood is chosen as the correct class label. And when you apply gradient descent to find like the closest different label, I show you some images here on the right-hand side where the images that you see are exactly at the decision boundary. So for the first image, you see it's an example. The probability that this is classified as a 0 or as a 6 is exactly 50%. For the next example, it's between 1 and 2, then between 2 and 7, 3 and 7, and 4 and 9. And so this actually looks quite similar to also how a human would be uncertain about the classification of these images. And this property has been analyzed in a very recent paper much more precisely by using so-called controversial stimuli. So what you do there is that you can compare two models, A and B, as is shown on the left-hand side. So the response of two models to different stimuli, and you can search for stimuli that exhibit the strongest disagreement, for instance, in this diagram. So the x-axis would show like the probability for a 7 given the image minus the probability for a 3 given the image, and for both models. And on the red diagonal, you see that's basically the diagonal where you have the strong disagreement, and the far out you are, the more controversial these stimuli are. Now you can test in a pairwise fashion, or you can search for each pair of images for images that are most controversial between these two images. And what you see then is that for our model, the controversial images actually, or that humans actually agree with our model that these are the 7s rather than 3s. And here, on the other hand, when these are 3s rather than 7s. So as a last example, I want to mention a work on invariance testing. So in addition to adversarial examples, which basically are examples where minimal changes in the images lead to different machine perception, but keep the human perception constant. In metameric examples, you have humans perceiving very different things while the machine sees the same. And with invertible neural networks, you can easily generate pre-images where the logits, the output that you are using for the classification are completely identical, but you just change the remaining nuisance parameters. And you can see that even though all these images that are generated with exactly the same outputs look very, very different to humans. And so usually when we don't use invertible architectures, we throw away a lot of information, and that's this information that we throw away actually corresponds to the type of invariances that the network is using also to generalize. And so in an invertible neural network, we have this nuisance space that is typically thrown away. We make this invariance manifold explicit such that we can explore it. And so the examples that I showed you can be seen like this. So for instance, for ImageNet, we have a bit more than 150,000 input dimensions and thus also 150,000 output dimensions. And only 1,000 of them are used for the classification, and 150,000 are then the nuisance space, the invariance manifold. And for MNIST, we have something like 784 dimensions. 10 are used for the MNIST classes, and 774 again span the nuisance space. And so the way how to generate these images, these pre-images, is by combining, say, the 1,000 dimensions of the signal image shown on the left-hand side with the 150,000 dimensions of the nuisance space shown on the right-hand side. And as you can see, the pre-images look more or less exactly the same as the images from which you took the nuisance information. And the same is true for the MNIST images. So that shows the big difference between human decision-making and machine decision-making. But now, as we made this nuisance space explicit, we can try to minimize the mutual information between the nuisance space and the labels. And by doing that, we can significantly change the behavior of the neural network. So here you can see, again, examples on the lower row showing the nuisance images, and at the top row, the signal images. And for a standard learning paradigm, the pre-images would look like the nuisance images. But if you minimize the mutual information between the nuisance space and the labels, then the pre-images start looking like the signal images. So basically the signal space captures now the perceptually relevant information. Okay, that brings me to the end of my talk. So I've been mentioning a couple of attempts to show basically how the standard learning paradigm of minimizing the test accuracy still leaves room for lots of different decision-making rules that achieve high performance on the test set, but yet allow for very different strategies to solve that problem. And the question is what kind of tests allow us to come up with more constraining solutions such that the resulting neural networks rather match the decision-making behavior of humans or of our intended solutions. And I think the goal would be to introduce better inductive biases in order to make this more effective. Thanks for your attention.
Oh, thanks. Thanks, Professor Martis, for your great talk. And can you end your screen share now?
Yes, just a second.
Okay. So our next part is the panel discussion. And yeah, as we mentioned before, like there are two ways for asking questions. The first is that you can directly ask a question via the Zoom. There's a chat button there. So you can put your question in there. And also like you can raise your hand and we can unmute you to let you ask questions. And another way is that you can go to the Slido website and you can put your questions there. Okay, so, and yeah, in the panel discussion, we have the first speakers here, Professor Alan Yu, Professor Alexander Madry, Professor Ilan, and Professor Martis. So yeah, let me unmute the Alan first, sorry. Or Xin, can you unmute Alan for speaking?
Yeah, I unmuted Alan, I think.
Okay, you can hear.
Yeah, we can hear you now.
So our our four speakers are here, right? Like,
I think so.
okay. So maybe let me start the question. Like for Alan, your talk is about the occlusion. For Marjorie, your talk is about the dataset statistics between like different datasets. And Jens, you're talking about the adversarial attacks like on object detectors. Professor Martis, you're talking about the generalization, how to test that. Like, do you think like these questions in the high level, like they're really looks quite different to your testing scenario? Do you think like they are closely connected or? Yeah. So Alan, can you start first to?
Sorry, there was a small cutout in the middle. I mean, you're saying that the talks were rather different?
Oh, no.
You're saying?
Oh, I'm asking like, for example, you're talking about the occlusion things, right? And the Professor Marjorie are talking about some dataset statistics. And Professor Jens are talking about the attack on the object detector. Professor Martis are talking about testing generalization. Like, can this question all be like in high level related, say, because your testing scenario are quite different, like, and like, do you think like they are closely related to each other?
I guess I can start just to get things going. I mean, I would say that they relate fundamentally to the enormous space of images and the fact that the data sets individually are not big enough to deal with them, and we have to come to terms with all these issues. And the adversaries are a very nice way to effectively expand the space of images that we're testing on. And I think that's extremely important aspect of vision. So what do the others think?
Yeah, just to add on this, like, so to us, like, you know, like, okay, to me, the question of robustness is the question, like, how to learn reliably using our tools. And for that, like, we need to understand, you know, how much of this is coming from our training methods being not, you know, being not appropriate versus, you know, like there are us hitting some fundamental barriers in terms of how our data sets are constructed. Right, so this is where our work came from, just saying, okay, before you try to, like, you know, innovate over adversarial training or something, like, just understand what are the limits of what our models are able to learn from the data sets we are testing them on, and, you know, how does it differ to, like, how humans learn? Because in the end, the question for robustness is really the question of, like, how different machine learning kind of vision is, you know, is like how much does it differ from human vision? So to me, trying to go all the way to the core and thinking about, like, what can we even hope to learn from this, given the bias that exists there, that was where our work fits into.
I see. So Professor Jens, do you have any like comments on this question?
Yeah, I think, I mean, I kind of agree with what was said already. I mean, especially from a, you know, from an attack perspective, in a sense, like, I view all these attack algorithms as kind of data generators, you know, in the sense that, okay, we get a sense of what these attacks are going to look like in maybe in terms of these images. And, you know, that can probably be helpful in studying how our natural training sets that we collect today, how they might be different from what these attacks look like.
I see. Then Professor Martis, do you have any comments on this question?
I think I would add that I think one of the maybe biggest discrepancies is that we tend to use discriminative models most of the time when we train on ImageNet. And the type of tests that we are doing, like occlusion and so on, they actually use quite explicitly the qualitative physics of the world, right? And I think that also the way how we generalize is by understanding particular, like the grammar of how objects can be combined to new objects and so on. And this is not very well represented in the typical architectures that we are using. And so the non-robustness properties that we are seeing, I think, is due to a lack of capturing these qualitative physics, these visual grammar type of aspects that would allow to generalize, and also completely out of domain.
Yeah,
I see.
I would second that. I mean, I would go ahead with that, and I'd say also, for me, a problem with the current data sets is that they set up a situation where people just try and train discriminative models because they're able to deal with them. But really, if you go out of domain or do harder things with more complex adversaries, then you're giving it a far harder task. And this is my bias, but my long-term perspective is we won't solve vision until we have good generative models. And we ought to be having data sets or tasks that would evaluate those rather than methods that you can solve purely by doing regression. You know, we know how to do regression, but it takes us some way, but it doesn't take us nearly far enough.
I see. So, okay. So we saw one audience email from University of Bristol ask a question. I'll unmute you, so you can ask your question there.
Thank you very much. My question is related to the pipeline that Professor Madry had presented about how datasets are created, which is we have one task, we choose certain concepts, and then we go and search for examples that allow us to create a balanced dataset. There is currently two new trends. One is to collect one dataset for multiple tasks, like the taxonomy approach. Another is collect data for no tasks. So just collect as much data as you have and then see what you can create with it. That, though, results in clearly unbalanced datasets. So datasets such as Elvis for the latest one for segmentation. We created a dataset on video understanding. So that gives you a rich dataset in the sense of data is collected before tasks are decided, but the unbalance automatically happens. What do you think about this alternative? Is it a way to go, or is the balance a critical requirement?
Yeah, so that's an excellent question. And, you know, like, so I definitely, so the problem here is that like our current data sets is like they're convenient to have them balanced for many reasons, but just this balancing alone is already like, you know, it's not ecologically valid. Like this is not how, you know, like our vision works. Like we don't see that many breeds of dogs. Like probably like I have seen maybe like at most like 40 different breeds of dog in my life, you know, like essentially as a human. So essentially like, yeah, so it would be an interesting approach where we kind of like imagine you kind of record a video of like a human walking around the town for like a week. And based on that, you create a data set, you know, so like, yeah, we are not creating this ourselves, but this would be a very interesting approach to do it because it definitely would get closer to this kind of ecologically valid way of data set construction. So yeah, I like this idea.
Okay. Yeah, so we get another question from Nathaniel Ruse. So you can ask your question there. Thanks.
Hello, my name is Nathaniel from Boston University. This is a question for Professor Betch. So my question is, there are some other classes of kind of machine learning algorithms, such as capsule networks proposed by Jeffrey Hinton. And this is more like a question about your intuition about the future, is whether we need these new classes of algorithms or whether, you know, fixes such as getting data sets like stylized ImageNet and the invertible deep networks would kind of fix the architectures that we have right now to more closely model human perception.
I don't think that like data augmentation alone would solve the problem. Obviously, I guess nobody knows. I think if one can get quite a lot of improvements by providing more information, maybe by, for instance, by introducing semantic bottlenecks, doing attribute learning, and trying to learn intermediate features that are more generally useful. But I guess my personal hunch is that I think it's also necessary, or at least very promising, if we make progress on building different architectures. I mean, one thing that is quite obvious is that, for instance, the background information that we tend to use in a rather similar fashion in these discriminative architectures, it would be very good to segment them out and do this in a very principled fashion in typical object recognition tasks. So we have a clear distinction between foreground and background. And that's just one of the many things that we know and that we have worked a lot with, but we haven't fully translated into, say, effective architectures that do this on a general basis. So okay. I guess I think like using generative modeling ideas will improve and will be important for building better vision models.
Okay, thanks, Professor Matthias, for answering this question. We are asking, is that you? Or like,
yes.
Yeah, you can ask a question there. Yeah, thanks.
Yeah, thank you, Zhihan. So my question is regarding domain adaptation and how this technique will fit into this panel discussion. Given the background, Professor Manjin talked about dataset bias and model bias and real-world application. The translation has been a long-standing problem domain adaptation tries to solve. The way it does it is to review some unlabeled data of the target domain during the model training stage, such that the model could potentially account for the target scenarios. Not only the dataset bias, also want to see how domain adaptation could fit into the adversarial robustness in general. Thanks.
Yeah, so I'm not sure there was a particular person that was supposed to answer, but like, let me just take a stab. Yes. So in some ways, yes. So again, so maybe one thing to say to set the stage that like what we discover in our work is that actually like in some ways, instead of thinking of robustness as an end goal, you can really view as robustness as a way of like trying to understand, how different, the way machine learning models solve the given task is to how humans would solve it. And kind of adversarial example in particular are a way of seeing the difference. Like essentially, whenever you figure out some correlation, some bias of the model that humans don't have, that kind of is likely to give rise to adversarial examples. So to me, for example, adversarial training is all about, encoding kind of stronger human-aligned prior into the model. So domain adaptation would be another way to do this, like kind of essentially with domain adaptation, even though you use unlabeled data, you kind of tell the model how the world outside of the distribution it has seen actually looks like. And this is in particular like the important goal of the models is to get disentanglement of certain features. So you would like to really like kind of it had this kind of higher level representation of like what are objects and what is background and so on and so on. And essentially like providing more information via domain adaptation could be a very viable way to do it. So in particular, we do know that you can leverage unlabeled data as a part of the serial training to get more robust models, but I think there is more to be done there exactly by like building on the domain adaptation work.
Okay, yeah, thanks for Marjorie for asking this question. And we got one question for the Professor Edens. There's one question from the Slido asking, have there been like security incidents in the real world where a bad actor can use, say, adversarial eyeglasses or stop sign stickers to fool facial recognition or self-driving cars? Do you know any such things happened before?
So there are a few interpretations to that. I mean, one interpretation of the question is, has there been a real security incident of some malicious person trying to do this attacks on face recognition or other things? To my knowledge, no. I have not heard of anything like this. However, there are several demonstrations coming up. They may not be exactly adversarial examples, but they do demonstrate some end-to-end effects. So one example is this attack I saw a while ago where they make a 3 look like an 8, like a 30 speed limit. They put a tape and extend it out. It's not exactly your adversarial example in kind of the definition that we have kind of borrowed from the digital world, but it does show an effect, an end-to-end effect in some sense. But beyond that, I do not know of any actual malicious attacks in the style of adversarial examples that that we think about here in these papers.
I see. Thanks for this question, for this answer. Yeah, I think you should, like, you have another meeting, right?
Yes. So yeah, thank you again for the opportunity, and happy to participate.
Yeah, thanks for participating in this panel. Thanks. Okay. We next ask the Motasin. Like, you can like ask a question here.
So yeah, I'm Motasim. I'm from KAUST, and I would like to ask Professor Madri. So first of all, thanks for his talk and emphasizing on the role of the dataset and the leveling of dataset into the generalizability and robustness. But my question is like, what is the key important path to go? Is it trying to fix and build up new enhanced or what's so-called datasets? Or is it trying to design better loss functions, or like in the sense of the robustness problems? Or is it even trying to introduce new training schemes, or even designing better architectures, or transforming the problem into another domain, something like Fourier? Like, because I think the problem is just more complicated than looking to one of these factors independently. But what is like the key path that one should tackle to at least to have like a significant progress?
Sure, great question. So the answer will not be very kind of surprising. The answer is all of that. Like essentially, like in the end, so what our work showed, that definitely there is a work to be done in the context of datasets, that we need more rich and better annotated datasets. That's for sure. But like this alone will not help. Like we have to have more algorithmic ways of improving our priors that our models have, and how to make them more human aligned. And this is like a question in neuroscience in particular. And Professor Bette in particular, is working on this kind of stuff. And so there is a lot to be done there. It's like if you think of humans, like the amount of footage that that an infant is exposed to is not that much by our ImageNet standards. If you think of it, so they have something nice, like our brains are good algorithms that are able to have they have some, like, of course, embedded prior, but also like the algorithm that governs our learning has to do something right about enabling us to get this like robust understanding of the concept. So to me, like this field is very exciting, because exactly like everywhere, we need to make advances. We are definitely at the beginning of the path. It was just felt to us that like people don't appreciate enough the data set aspect of it, and that's what we wanted to highlight. But doesn't mean that this is the only thing we should be focusing on.
Okay, thanks Professor Marty for answering this question. And we got another question for Professor Alan Yu. And the question is, for the adversarial attacks in the physical world, like they're creating some adversarial patch, do you think like this one is somewhat related to your occlusion? Like you talk about occlusion, like do you think like what's the relationship, and is there any common solution to solve both these two things, like say robust to occlusion and robust to adversarial attacks in the physical world at the same time?
I think they're very related problems. I mean, because, if you take, you modify patches a bit, they start looking like objects, etc. Certain patches, perhaps a little bit more abstract. But yeah, I think they are very similar, and they, they give rise to similar defense problems. Our own work has concentrated on defending against occlusion, and I think we haven't tried that out for defending against patches, but I think it would work reasonably well to defend against certain parts of patches. Although, yeah, we need to let you know by the end of the summer. So I agree with you, and I think similar defenses would probably be effective, though, even what we've done is only limited. I think one needs frankly, I think we need three-dimensional models. We need a whole lot of other stuff into these networks. So in terms of the earlier questions, I'm very much on the side of thinking that the current networks are not enough. We need a lot more inside them, as well as better data sets and better evaluation methods.
Okay, yeah, thanks Professor Allen for answering this question. I'm unmuted another person, Peng Rui Quan. You can ask your question here.
Hi, this is Peng Rui Quan from UCLA. I have a question for Professor Matthias Berger. So in your talk, you illustrate many perspectives of adversarial examples. For instance, when we generate an adversarial examples of cat and we ask an image classifier to train on that examples, then the classifier start to memorize some image feature of a cat. And another perspective would be like the classifiers focus very much on the texture information instead of the shape information of a class. So I'm wondering from your perspectives, what is essentially causing the adversarial examples in the vision task?
I mean, I didn't intend to explain adversarial examples with this different biases for texture and shape. So I just highlighted a couple of differences between machine and human vision. And so texture and shape is two different types of cues that we can intuitively assess and we like to distinguish. And it's easy to, well, we can classify decision algorithms in their degree to what extent they are relying on texture information or on shape information. And there seems to be a tendency to using texture information, which is probably due to the fact also that texture gets a lot of pixel support, right? So you have a lot of input dimensions that define the texture, and it can be less precise. It's more like this back of feature approach. And but I think the adversarial examples, they also look a little bit like the changes that you impose on the images also look a little texture-like, but I think there's so many room for all kinds of features that we don't quite understand that these networks can be using, that I think we are not really there in being able to explain what an adversarial example really is or what kind of decision rules used there.
Okay, thank you very much. I'm just wondering if we can understand a little bit more about the image features of the adversarial example. Perhaps we can utilize that features to design more efficient attack or defense mechanisms. But thank you very much for your illustrations.
Yes, thanks for asking a question, and also Professor Matthias for answering this one. I will unmute the Adam. Yeah, you can ask your question. Thanks.
Okay, cool. Thanks. Hi, I'm Adam. I'm a postdoc in Alan's lab. And it's really nice that Alan and Matthias kind of agree that we need generative models. And all of you three have said that we kind of don't evaluate discriminative models and we correctly, and it's like really difficult. Then on the other hand, if we want to have combined models like discriminative and generative models, then, you know, if we look at the generative model literature, they also really struggle on how to evaluate generative models correctly and, you know, how well they generalize. Now, if we have like combined or hybrid models, this would be like kind of double as difficult to evaluate. So is there any chance that we will be able to evaluate them correctly? You know, are there any opinions on this?
Well, you know, like I think that actually, like in some ways, they are like to me generative models, and like a real evaluation of discriminative models is kind of just two sides of the same coin. And in some ways, actually, if you are managed to kind of to like have like, so this is kind of the work we had, that like when you can use a classifier to actually get generative model, that actually might make it easier to to probe what they are missing. Okay? So if you can ask my classifier, oh, can you tell me what is your concept of a dog? Like, can you give me a random, like how a dog looks like, based on the features you have, and then you can see, okay, does it have, 4 paws or maybe some different number? Does it have 2 ears or some different number? Like essentially, like if you can ask this question to your classifier, it actually makes it easier to evaluate in what way it might misalign with what you would like to do. So it might be one of the things that once you ask for more, it's actually easier to verify that it does what you want.
I see. Yes, but how will you ever be able to evaluate if it knows how all dogs in the world look like?
Well, that's the generative model what gives you. If you can sample from distribution of dogs, then essentially you will at least get an idea. Of course, not like this is distribution. You will never be able to inspect it, all of its support, but at least you will be able to get some idea of like some, more significant trends.
Yeah, sure. So I think this would be like for now enough.
Well, I think that's where we should go. If it will be enough, that remains to be seen.
Thanks. Cool.
Yeah, Alan, do you have any comments on regarding this question?
I can talk with Adam about this on
Okay.
because I think you need to have a series of different questions or different tasks, and so having algorithms that don't just perform one task, don't just do well on ImageNet, but do well on transferring from ImageNet to some other data set, or which work on ImageNet and then also work if you change the background dramatically. So I think having that class of tasks are important. Another thing that was harder to say is that I mentioned adversarial examiners in the talk, but there's also the ideas of visual Turing tests that the Don Geeman and his brothers sort of talked about. Ultimately, you'd like to be able to answer any question about the image that a human could ask. And so if you could set up those types of challenging tests, that I think would be something which, as a person in the generative camp, I believe will demonstrate the values of the generative models. And so I think harder tests of that sort, and why I really like the adversarial stuff is because it sort of brings that out. You're not just testing on a fixed data set, you're sort of allowing other images to be created, that are not in your data set and see if they mess up your algorithms. So I think we need to move a lot more in that direction. And I think as a reviewer of some opinion paper I wrote said, the computer vision community has been incredibly lazy or not making challenges of that type. We're still working in this rather slightly boring, balanced training testing set, and that was great for the last 6 years or so, but I really think it's reached its sell-by date, and we need far more interesting and advanced types of tests to move forward.
Okay, thanks for answering this. Professor Martis, do you have any other comments on this part, like how to properly evaluate those things? Hello, Professor Martis. You can unmute yourself for answering this question. Do you have any comments on this?
I first understood you asking Professor Madri. I don't think I have a particular comment right now. Sorry.
Okay. Yeah. I also saw one question from Professor Tom Dietrich asked the question in the Slido. That's for Professor Alan Yu. How do you constrain an adversarial examiner to within the space of rare image? Because you mentioned the adversarial examiner work.
Well, we've only had, I guess we've had one paper on that and another one, well, you can count on that, that's under review. The paper that I mentioned is one where you use computer graphics to generate the images. And computer graphics is very nice because you can control all the factors and you can vary viewpoint and so on systematically. And if you ask questions directly, I mean, by the algorithm we had or other better algorithms, you can sort of search through this enormous space in an intelligent way to try and find where the algorithms, break down. It does rely, admittedly, on being able to deal with computer graphics type stimuli, but on the other hand, as a believer in domain transfer, I'd almost say we should be requiring our algorithms not just to work on real images, but they also work on computer graphics images as well. So I don't really see that as a limitation. Do I care about absolute realism in putting patches on it? Well, I mean, I guess I would say as somebody who's half in the cog sci department, if a human can do it, I want the algorithms to do it also. So even if it doesn't look terribly realistic, but the human's got no trouble dealing with it, then I think the algorithms should be able to deal with it also. Because why can humans deal with it? Because potentially it's, it's an aspect of our visual system that's really good, and we ought to be having algorithms that have got the similar capabilities.
Okay, yeah, thanks Professor Allen for answering this question. We will let one audience for ask the last question. Manju from IT. Yeah, you can ask your question here. Yeah.
Okay, thank you. Thank you everyone for the great presentation. So my question is related to bias. So it might be more towards Professor Madhuri. So right now, I think some people, many people are moving towards like debiasing methods in developing models which are less, which can even handle like bias scenarios. What do you think of that direction? Also, people are also trying to do some sort of like, disentanglement of trying to disentangle different factors and trying to get sort of like concepts. And do you think will that help in sort of like, trying to find only like a suitable concepts so that it will not focus on like unneeded concepts when you are doing this kind of disentangling operations? So my question is, what are your thoughts on those kind of approaches right now?
Well, they are definitely like, going in the right direction, right? Like, again, like disentanglement is kind of, a kind of, a word, like a kind of, like this just means that like, yeah, we want to, like, we know that certain concepts should be disentangled and they want our models to get that. So clearly, again, the moment we make the decision-making of our model more closely resemble ours, this is clearly a progress. The biasing approaches in general, especially in the context of fairness, of course, I would say their kind of scope goes beyond robustness, because in some ways they want to also debias things that even humans, or especially humans, have biases on. But yeah, again, this is a very important work, because like that's what we need to do. We first need to diagnose biases, and again, I focus more on the biases of that correspond to human vision and kind of how human perception works. But there are others, so you need to have a toolkit to identify them. But then you need to think how to correct for them. So yeah, so I think this is exactly one of the key challenges in machine learning right now, is exactly like how to go beyond what we can just blindly infer from data. How can we be more retrospective about what we learn and adjusting it retroactively? So yeah, I'm very much looking forward to what this kind of strand of work will give us.
Okay, thank you.
Yeah, Professor Martin Spassky, do you have any like comments on adding this? Because like the biasings are kind of related to your like CNN trained ImageNet trained CNNs are biased to texture, and you use some style transformation to make the model biased to shape.
Actually, I wanted rather to comment on the disentanglement. So I think if you think of scale invariance, so this is an operation that we know, a very simple one that applies to any object. So if we change the scale, it generates a lot of changes in the pixels, but the semantics stays exactly the same. And if you want to learn that from data in a typical ConvNet architecture, and you learn it for, say, 10 different object classes, it wouldn't generalize automatically to all kinds of other object classes, right? So it's the architecture is not designed that you can factor out the scale invariance directly. And so obviously one can impose such, say, scale equivariance in a hard-coded fashion. But it's one of these examples where when you understand invariance property that we are using all the time, if you want to learn that from data, it's actually quite tricky, and like factorizing out these transformations that suddenly allow you to generalize much more and reduce the learning complexity is, I think, an extremely important task, because in the end, learning is always like a combination of prior knowledge with data, and the amount of data we have is, even if it's 1 billion or more, it's really nothing compared to the curse of dimensionality. So we really need good symmetry assumptions and inductive biases, right? So I think we need more of exploring that.
Yeah, thanks for answering. Alan, do you have any more comments?
Well, I guess, infinite images, combinatorial explosions. I think finite data sets are out, no good, etc. But I'm probably repeating myself. I don't think that just having more data is going to help. Better algorithms are needed. Better ways of testing performance are needed. Richer classes, and like I think many of the other panelists, I think I believe that seeing what humans can do and understanding that is going to be very important, particularly if we want computer vision systems that work at human level, which frankly we're nowhere near, despite some people who are getting a bit over enthusiastic about it.
Okay, yeah. Okay, so yeah, thanks, Professor Allen, Professor Alexander Marjorie, Professor Yelens Fernandez, Professor Martis Besky for like attending this panel discussing, and also for all audience for asking the question here and yeah, getting involved here. And yeah, the panel discussion now is over, and we next will be moved to the poster session. Yeah, for the poster session, like you can find the Zoom link. One thing I want to correct here is that you cannot go like enter the Zoom via our external website. You can only enter the Zoom in our internal website. So yeah, so just enjoy yourself and talk to those posters. And yeah, that's all. Thanks.
Thank you very much.
Yeah, thanks for attending. Yeah.
Thank you for organizing this.
Thanks.
Yeah, thank you very much. Yeah.
Yeah, thanks. Okay, hi everyone. Welcome back to our CVPR 2020 Adversarial Machine Learning in Computer Vision workshop. Our next speaker is Lawrence van der Matten. Dr. Lawrence van der Matten is our research director at Facebook AI Research in New York. He received his PhD from Tübingen University, the Netherlands in 2009. With collaborations from Cornell University, he won the Best Paper Award at CVPR 2017. Lawrence is interested in a variety of topics in machine learning and computer vision. The talk today is Adversarial Robustness, the end of the early years. Lawrence, you can unmute yourself and yeah, thanks.
Thank you. Thank you, Sihan.
Thank you.
Is the sound okay for you guys?
Yeah, I can hear you very clearly.
Awesome. Excellent. Thanks so much for the kind introduction, Sihang. I'm really excited to be here. I must say I'm also a little embarrassed, and I'll tell you right away why. Because I've sort of, over the past year and a half, I've basically stopped working on adversarial robustness, and so I really feel like an outsider in this workshop. So what I'll try and do in this talk is I'll try and give a little bit of an overview of some of the work that we did in adversarial robustness. And then I'll try and reflect a little bit on sort of my thoughts on the field overall, and in particular, why I stopped working on it and what I'm working on now. So I hope that that's okay with all of you. So maybe to get us started, right? Like I'm sure many of you, or I'm sure all of you are aware of sort of adversarial examples, right, or adversarial images. I think this was the example that drew me into this field. Was this example of semantic segmentation? This comes from a paper by Mustafa Cissé and co-authors, where they managed to fool the semantic segmentation algorithm into predicting this minion, which isn't just entertaining, but also raises a lot of questions, right? And the questions are around, if you can do this with small perturbations, like what does that tell us about the networks, right? Like, can we learn something about convolutional networks or other deep learning models by studying these adversarial perturbations and this limited robustness? And the other question is, of course, a security question. Does this raise concerns for practical computer vision systems, in particular if those are systems that are used for instance, filtering objectionable content on large social network websites? And so we started looking into this field a little bit in 2017. I was pretty excited about this, right? So we started looking at these kinds of examples, right? Like you take an image of a ladybug, you produce some kind of adversarial perturbation, and suddenly the label, the predicted label of the network starts changing. And in a lot of these cases, we have some measure of attack strength as well, where we could measure the attack strength, for instance, in the size of the perturbation that is applied. So we were, we were mostly interested in sort of the defense side of this problem. So like, how can you train models or develop models that are robust to these kinds of perturbations, right? It's clear to humans that the content of the images, the semantic content isn't changing. So it feels like they should be possible. And so we started off by basically asking ourselves the question that I think any computer vision researcher should occasionally ask themselves: what would Alyosha say? And Alyosha would probably say, well, did you try nearest neighbors? The answer at that point was no. So we figured, okay, let's try something with nearest neighbors and let's see what happens. And in particular, we used very old work by Alyosha and Bill Freeman called image guilting. This is a paper from 2001. And I'll explain very briefly how it works. So in image guilting, what you do is you create a database of image patches, so small, like 3x3 or 5x5 or 7x7 patches, And what you're going to do is you're going to scan the original input image. And for each location in the input image, you're going to find the nearest patch in the patch database. And you're going to put that patch in place on the right side in your cleaned image. And now these patches are overlapping. And so in overlapping parts, you're going to do a graph cuts algorithm in order to sort of find the optimal seam between overlapping patches. And if you do this for all the patches in the image, then you get something like the image on the right, which is a cleaned version of the image on the left. And it's made up only of patches that come from this patch database, right? And the patch database you filled with patches that come from real images, right? So images without adversarial perturbations. And our hope was that a lot of this, that this algorithm would basically remove a lot of the fine-grained noise or perturbation that the adversarial examples create, right? And so our sort of defense mechanism, the way it worked is we would take an input image, an adversarial input image, we would clean that image up through the image kilting algorithm, and then we would feed it to our convolutional network for prediction. And we tried this out against two adversarial attacks that were popular at the time, Deep Fool and the Carlini-Wagner attack. And what I'm showing here is the accuracy of the network as a function of the strength of the adversary, as measured in terms of the L2 norm of the adversarial perturbation. And so higher is better. And so what you see is that these attacks are quite effective, right? The dashed line is showing you that as soon as you apply them and there's no defense, then almost all images will be misclassified. The light blue line is the line that you get from image kilting, and what you can see is that it's definitely lower than the accuracy that you'd get on clean images. But the line is pretty straight, right? And so, even as you increase the size of the perturbation, you continue to get reasonably good classification accuracies. This is for a ResNet 50 model, and so at a 0.08 attack strength, we still had around 65% classification accuracy, which is not bad. So this kind of seemed to work. But of course, Carlini and Wagner, since they developed this attack, they had to, sort of come back at us. And they published this really interesting paper where they showed how to circumvent a defense like this in the white box setting. And sort of their main idea is that because the cleaned image is very similar to the original image, what you can do is you can basically change the attack to evaluate gradients not at X, but at the the cleaned version of X, right? So basically, they would run the image kilting algorithm using the same patch database as part of their attack, and they showed that this is really, really effective, right? And so these kinds of defenses, like this image kilting defense, is something that may work in sort of a black box setting. However, if the attacker knows about this kind of defense, like it's relatively easy to circumvent this, right? And so, this line of work was in that sense was unsuccessful. The second thing we tried is we looked at a combination of adversarial training and feature denoising, and this was work by C. Hang, who's one of the organizers of this workshop when he came to intern at Facebook about 1.5 years ago. And basically what he did is he looked at adversarial training. So this is this really old idea that already appears, I think, in work by Ian Goodfellow in 2015, where the idea is to train the network on adversarial images, like at training time. And in that way, develop networks that are robust to these adversarial images. And he was combining this with an idea called feature denoising. And so the idea in feature denoising is that if you look at the feature maps of a convolutional network, when you apply an adversarial perturbation to the input, what you see is you see that the magnitude of the perturbation in the intermediate feature maps is growing sort of as you get deeper in the network. And it leads to this kind of noise that you see on the slide here. So if you feed a network a clean image, you could get a response map like the image on the top. But then if you feed an adversarial version of the same image, you get the response on the bottom, where you see all this noise sort of in the background of the object. And sort of our hypothesis was that this noise is the stuff that we want to filter out. And the way we tried to filter this out is by basically including blocks in the convolutional network that do a kind of non-local means. I'm sure many of you remember non-local means, right? It's this idea of basically filtering an image by computing a similarity measure between a pixel I and all the other pixels j. So that is the function f here, and so this could be something like a Gaussian kernel, and then using the resulting weights to compute a weighted average of all the pixels and put that in the location of pixel I. And this is an operation that you can relatively easily implement in a convolutional network or in any sort of deep network. So the basic idea is that you take your image as input, you flatten the image along the height and width dimensions. You compute a kind of basically you compute all inner products between these in this case 256 dimensional vectors, right? So this gives you an HW by HW output map. So this is the evaluation of f in the equation on the left, and now you use these weights to basically reweight another version of the input x, and so that is the multiplication between f and x as well as the summation. And so this blue box here is basically implementing non-local means. And then what we did is we put non-local means in a very simple residual block, which is the white area around it. And so what we observed qualitatively is that these feature denoising blocks, they remove perturbations or they remove noise from the feature maps. So what you see here is for a few input images, you see a feature map before the denoising block and then the corresponding feature map after the denoising block. There is a natural ordering in these activation maps because we use residual connections. And so we trained models that contain these denoising blocks using adversarial training. And the results that CHANG got look like this. So here on the x-axis, you see the number of attack iterations in a PGD attack. And so CHANG went all the way up to 2000 PGD attack iterations, which is a very strong attack. And we're showing a couple of lines here. In particular, the orange-red line is a model that is just trained with adversarial training. And then the yellow line is the same model with the additional denoising blocks. And so what you observe here is two things. One, actually, that the red line is a lot higher than prior published work at that time. And the reason for that was that what we realized is that if you use many more attack iterations during adversarial training, the adversarial training algorithm actually becomes much more effective at the expense of a large amount of compute. And that's maybe where the caveat is. And the second part, the second thing that you can observe is that the yellow line is consistently higher than this red line, and so these feature denoising blocks they really seem to help a couple of percent. And so I think actually these results are still state of the art. They were definitely state of the art when they were published. I haven't followed the field super closely, so I may not be familiar with all the latest and greatest results. but I think it's fair to say this is still among the sort of the most effective defenses out there. And, so it'd be really easy to, go out and celebrate and sort of think it works. But there are a couple of caveats, right? If you look at these plots, one of the caveats you already see is that, even though these defenses somewhat work, a classification accuracy of 40% on ImageNet is not, is not great. The second thing is that these models are very computationally intensive to train, which is a downside. And the third thing is that in order to get this accuracy on adversarial images, we actually pay a price in terms of classification accuracy on clean images, right? And so if you were a large web company and you were running image classification as a service, then that would be a major problem, right? If 0.01% of your images is adversarial, then you maybe don't want to pay a very large price on the 99.9% of clean images that you have to classify. And there was one other thing that that sort of, as we were working on this, started bothering me, and that's sort of this question of, are we solving the right problem? In particular, if you look at a lot of the work in adversarial robustness, it makes a set of assumptions, right? And probably some of the main ones are one, that the perturbation that we apply has a small LP norm, which may seem sensible, but then if you think about it, there are a lot of perturbations that you could apply to an image that will not change the image's semantic content, but they will have a massive LP norm irrespective of what P is, right? So for instance, if I'm going to add 2 white lines to this image, we as humans still see the exact same thing on this image. We basically ignore these 2 white lines altogether. But we've applied a perturbation that is very large in the LP sense, right? And so I think really what is sort of much more interesting in a lot of practical scenarios, in particular in scenarios where you're trying to develop filters for objectionable images, is sort of a type of perceptual norm, right? Like the adversarial perturbation should have a small perceptual norm. The problem there becomes, of course, that nobody really knows how to formalize such a perceptual norm, right? A second problem, I think, is sort of this full white box assumption. I see where I understand where this comes from, right? Security by obscurity is not security, and so there's a strong sense in the community that you need to only work on this full white box setting. But at the same time, if I think about a lot of practical scenarios, for instance, if you were to run a large social networking website, you wanted to keep objectionable images from your websites, then the full white box setting may not be sort of the right assumption. If you had full access to the model and sort of all the code around it, then that website would probably have much larger problems than your adversarial images, right? And so in sort of those practical scenarios, I think it's much more reasonable to assume a kind of setting where you assume that the attacker has expert knowledge, right? So has sort of a good sense of what the model is that it's trying to attack. You could measure this in terms of some kind of divergence between the model that the attacker thinks it's attacking and the model it's actually attacking. And so a setting like that seems much more reasonable. But the third thing that really sort of got me working on something else was that I realized that you don't really need to be adversarial to break current systems at all. And this relates a little bit to the talk that Alexander Madry was giving earlier in the day, which I thought was super interesting. We did some work in that space as well. So what do I mean by this? What do I mean by you don't need to be adversarial? Well, so here's an example. Here are 3 images of soap, spices, and toothpaste. And these images were made in the UK and the US. And what we did here is we gave these images to a popular cloud vision service. And we got, pretty good predictions for these images. The predictions were toiletries, spice, and toothpaste. And then we took images of the same objects, except they were images originating from different countries. In particular, the soap was photographed in Nepal, the spices were photographed in the Philippines, and the toothpaste was photographed in Burundi. And suddenly these models don't work so well anymore. They recognize the soap as food because it looks different. They recognize the spices as beer because apparently in the Philippines, spice containers look differently from in the United States, and they don't recognize the toothpaste if it doesn't appear in the context of a white ceramic sink or anything of that type. And so we did experiments to dig into this more. And in particular, we used this data set called the Dollar Street data set, which is a data set that was gathered by a nonprofit called Gapminder that aims to basically with the goal of showing how different people live across the world. And it's a data set that has around 20,000 photos, and it contains 117 classes of different households, common household objects. And in addition to the photos, it also records, in addition to the class, it also records the country in which the photo was made and the household income of the family, of the household in which the object appeared. And so what we did is we measured the accuracy of 5 popular cloud vision systems on these images across the world. And what we're showing here is the average accuracy of those 5 cloud vision systems for images from different countries, where dark green represents an accuracy of around 90%, a yellow color means an accuracy of around 75%, and a red color means an accuracy of around 60%. And so what you see here is that in the US and in European countries, you see this dark green color. These cloud vision systems work really well. But then in other countries, specifically in Southeast Asia, Africa, and parts of South America, the accuracies that we observe are actually much, much lower. And I'm showing averages here for averages over 5 different cloud services because we don't want to call out one service in particular, but really these results are consistent across services, including Facebook's own service. We in the paper we present our own results as well. And what this data set allows us to do is it also allows us to look at accuracy as a function of household income. And there you see a trend where basically these systems work better in recognizing common household items that appear in high income households. And this is not just due to a correlation between household and country, because if you zoom in on India alone, you still see these effects. So what's going wrong here? Well, what's going wrong is that, or what's causing this is that a lot of data set collection relies on very Western services, on things like Flickr. And a lot of data set collection starts from English queries. And I think that's a large part of the problem as well. So for instance, if you go on Flickr and you search for images of a wedding, you'll get images like the ones that are shown on the top row of a bride in a white gown and a groom in a smoking or tuxedo. Whereas if you would search for the Hindi word for wedding, you'd get very different types of images of brides and grooms in very colorful attire. Similarly, if you would search for spices on Flickr, you find images of these plastic spice containers. Whereas if you search for the Hindi word for spices, you'll find images of spices in open containers that are visually very, very different, right? And so and this is an effect that you see basically in all popular computer vision data sets, where, due to the way that they are collected, they incorporate massive biases that leads to the kinds of effects that I was just showing. So let me wrap up. So I mean, it's very clear that the adversarial robustness problem is still far from solved. But sort of over time, for myself, I've developed these doubts of, whether we are even working on the right problem, or is this more of an academic curiosity? And I think in particular, what I've been for myself a little bit disappointed about is that I think so far the study of adversarial robustness hasn't taught us a lot about how these convolutional networks or other deep learning models work. And I think that's where I had a little bit higher hopes for the field when it originally started. And I think, if you want to take anything away from this talk, it's probably that, you really don't need to be adversarial to break modern computer vision systems. You can just move to a different country, and that's kind of sufficient. And so I think from a practical point of view, there are these more urgent problems to work on, which is what I've been focusing my attention on. So finally, I want to thank a lot of awesome collaborators, people at Facebook, in particular Cheng Han, Ishan, Kaiming, Yushin, and Mustafa, as well as 3 amazing interns, Chuan Guo, Xiang Shi, and Terence De Vries, who did a lot of this work, and other collaborators like Ellen and Mayank. And with that, thank you very much.
Thanks, Lawrence, for this great talk. And then we can move to the next speaker.
Yeah. So our next speaker will be Dr. Pingyu Chen. So he's
yeah, Xin, you can.
So he is a research staff member at IBM Thomas Watson Research Center. Dr. Chen received his PhD degree in EECS from the University of Michigan. His recent research is on adversarial machine learning and robustness of neural networks. His long-term research vision is building trustworthy machine learning system. He received the NIPS 2017 Best Reviewer Award and was also the recipient of the IEEE Global Com 2010 Gold Best Paper Award. His talk title is Bridging Mode Connectivity in Loose Landscapes and Adversarial Robustness. So welcome, Pingyu, and you can start your talk now.
Okay, thanks everyone. So are you able to hear me?
Yeah.
Okay, yeah, so I want to thank again for the organizer for the invitation. I'm very happy to give a talk at this prestigious workshop. And I also hope everyone enjoys this workshop as much as I do. I never been so comfortable sitting on my desk and attending a workshop like this time. So the talk I'm giving today is bridging mode connectivity in lost landscapes, in particular for neural nets, and also the connection to adversarial robustness. And I'm Pingyu Chen from IBM Research. Okay, so this work is based on a recent publication that we just published at iClear 2020. Are you able to see my slides changing?
Yeah, we can see your screen.
Okay, sure. Okay. So it's that on the second page right now, right?
Yeah.
Okay, yeah. So this is, as I mentioned, this is a recent publication at the iClear. So with our IBM intern last year, Pu Zhao from Northeastern University, and his advisor, Xue Lin. The co-authors also include me and my colleagues, Payo Das and Katikanian Netherthin Ramamurthy. This paper not only get published at the iClear, also get some awareness from the public domains and get some media coverage, because we are trying to provide a very interesting and now I would say novel solution to sort of mitigate the adversarial effect based on backdoor attacks. So it's being included in terms of a larger news covering the space of backdoor attacks as well. So today you probably heard a lot about different types of adversarial attacks, right, that happened in different phases of the whole AI life cycle, and also happens in different domains like physical domains, digital domains, and so on and so forth. So here, before I dive into the detail, I would like to give you a holistic view of the whole adversarial robustness, right? So we can basically separate the whole AI life cycle into two phases, right? The first phase is the training phase, and the second phase is the test phase. And now these two phases also include the data collection, like how you collect the data to train your model, and also what model are we going to use to train on those data, right? It can be a neural net, it can be a decision tree or whatever. And once you have the model trained, you will deploy your model as a service, right? That makes it into the inference phase. And in the inference phase, you can also consider whether this is a black box function for inference, or you actually provide the whole details of your model for inference and for the users to fine tune and so on. In that case, that will be a white box model instead of a black box model. So with this picture in mind, we can talk about these attack categories, basically divided by to what extent the attacker can manipulate your AI lifecycle, and what are the attacker's objective, right? So for example, if you look at the poisoning attack, the goal is to inject some data to your training data and to make sure the generalization on whatever model will perform poorly. And you may or may not have access to the model you are going to poison, but you are going to inject some data. And you are not doing anything at the inference time once it is injected. So similarly, backdoor attack is one type of poisoning attack, but the goal is more stealthy. It's not going to try to degrade your generalization performance, but rather you try to inject some Trojan or backdoor to your system, and the vulnerability will only be revealed when a trigger is present in your data input. So it's basically only assuming the attacker can have ability to manipulate your data, and this can happen very often in scenarios like crowdsourcing data, and also in scenarios like federated learning. And in today, we also hear a lot of talk about evasion attack. Basically, how do you generate adversarial examples? In this case, usually you don't assume you have access to the training data, but you do need to play with the model at the inference time to do prediction evasion. And you may or may not have access to the model depending on it's a black box attack or it's a white box attack. And there are other attacks that are more security and privacy oriented, including model stealing attack. You try to steal a model at a cheaper price, or you try to steal the membership. In this case, you have to steal the training data by interacting with a black box model. And you can also consider other types of attack, like model injection, where you try to inject your own model at the inference phase and replace the function of the original model. And this can happen at the hardware level by playing with the bits that store the model and so on. So this is the overall picture of the adversarial robustness and what attacks can happen depending on the assumptions and the threat models you may have. So I would like to use some pictures to illustrate what the backdoor attack is, and that's basically the primary attack model that we are considering. And I figure I couldn't do a better visualization than what is provided in this paper by Bolan, Wang, and et al. Published at the IEEE Security and Privacy in 2019. So I decided to borrow their image. So the idea is pretty simple. You first identify a trigger pattern. It's basically a white square at the right bottom corner of the image, and then you add it to a subset of the training data, and whatever training data you add it to, you assign the target label to be 4. So this image is that with a trigger, you will be associated with a label 4 instead of the actual label. And other data that are not injected by a trigger will stay the same label as they are. And you use this basically poison model or backdoor model, whatever you want to call it, to train a neural net, then that make it a backdoor neural net. Very interesting, in the inference time, it is called a backdoor neural net because as long as this neural network memorizes this trigger effect, right? Whatever image you have, as long as you put the same trigger to the data input, it will try to predict as the label 4 instead of the true and correct label. However, it is a backdoor attack because without the trigger, right, it behaves just like a normal model, right? It will predict this image as a 5 and the other image as a 7 and so on. Let me put a highlighter or laser point. Okay. We also in iClear 2020 this year, we also extended this work attack to another regime that is in considering the federated learning setting. So federated learning is basically nothing but you have a bunch of local workers with local data, and they jointly want to train a global model. So federated learning provides a way to do federated learning by aggregating local information and train a global model. That sounds very ideal, but the fact that each local worker has its own local model and has its own local data actually makes the attack, a backdoor attack, more easily to happen. And in our recent work, what we show is that considering this pattern to be your global pattern, it's a global trigger with 4 squares. So what we can do is we can actually distribute this backdoor pattern by allowing each poisoned worker to have a subset of the global trigger. In this case, each poisoned attacker will inject part of the global trigger into its own local data set and do federated learning as is. And very surprisingly, by doing so, this distributed backdoor attack is actually more effective and also more stealthier and more resilient than centralized attack. This is intuitively, this is possible because each worker uses a weaker signal to inject the trigger pattern. So it's harder for the global model or whatever secure aggregation function to detect this is actually a backdoor model based on local model updates. Not to mention in the federated learning, each local worker will have some heterogeneity as a given. So it's very difficult to discern whether this is a normal or abnormal local model updates. So what we are showing here is a tiny ImageNet case where we consider some robust aggregation types and considering centralized and decentralized backdoor models. So as you can see, decentralized black box model are more effective in the sense that if you consider the number of rounds you need to poison the federated learning model, it takes much less rounds to make the attack successful, to successfully backdoor the global model and bypass these defenses. However, on the other hand, if you use a centralized attack, that means you use the whole global trigger to do backdoor attack, is more likely to be kind of eliminated by these effective robustness models. So basically, we are showing on federated learning schemes, this backdoor attack in a distributed fashion is a more practical and more powerful attack to consider. It can bypass some secure aggregation functions that are robust to centralized attack. This is just to give you a motivation on why we care about this defense against the backdoor attack. So now I would like to bring you to give you more intuition on why do we care about this issue, right? So this is all about model sanitization. So what do I mean? But let's start with an interesting question, right? So if I ask you, I have a very amazing ImageNet model which achieves 95% top 1 accuracy, and I would like to make it publicly available by releasing a model architecture and train the model weights. Or do you want to use my model for your own task? Right, so the general model developer will say, yeah, yes, why not? It's 95% accurate on ImageNet. I would like to use it for transfer learning or fine tuning or whatever. But a well-educated researcher, like the audience in this workshop, will say, hey, my experience from the CVPR workshop told me I should be aware that this model may bring some backdoor. Right? How do I know your model does not have any backdoor? So this is a very valid question. And so what we are proposing is actually, we still want to leverage the powerfulness of this trusted model, but we should use it by first sanitize it before using it. This is very similar to you have to wear your mask before you go out to protect yourselves before you do other activities. And this is a lesson to share with everyone, like, yes, so using models from trusted sources have risks of infection too. This is what happened basically for backdoor attack and also the federated learning setting that we just demonstrated. So here is our formal problem setup. It's basically can be summarized as a trusted fine-tuning with limited data. So we are basically given a model from a trusted source, which we know it may be potentially tempered by this backdoor effect. The problem is, can we only use a small set of clean and trusted data samples to sanitize the model, right? Because eventually we still want to use this potentially tempered model, but we want to alleviate its backdoor effect. And in practice, the size of this trusted data sample should be very limited, right? Otherwise, there's no incentive for you to use a risky model. Right? You may just use training from scratch if you have sufficient number of clean data. So this scheme makes more sense in a limited data regime. And I want to emphasize that this problem is really beyond detecting backdoor attack. We have some works on that, but we can save it for another time. So this is basically try to recover model instead of detecting the model is malicious or not. So I would like to take some necessary detour, right? So I mentioned the monoconnectivity in my title, but I haven't introduced what that is. So this is basically related to how the local minimum, right, in the loss landscape of neural nets are connected. So a very recent results have identified that the local minimum in the loss landscape of neural nets are actually connected by a simple curve function. So they are not only connected, their connection is in terms of the connection path can actually be characterized by a simple curve, where on the curve, the training and test accuracy remains constant. So here is actually an illustration of what that means, right? So here I have 3 different local minima that's trained independently on the same neural network architecture. So if you just do linear interpolation on their local minimum, the loss landscape are not connected, or you see some high loss between these local minimum. However, if you introduce some simple curve function, like here is a quadratic Bezier curve, or here this is another polygon curve function, you can actually find a curve along which the loss remains constant when you're connecting these 2 local minima. So this is what is called the monoconnectivity for loss landscape in neural networks. So how are we going to use these results to help us recover backdoor models? So this is the idea. So mathematically, this curve function that we are going to learn the mode connection it can be characterized by this parametric function phi theta. And you are given, basically, you are given 2 models, W1 and W2, and you want to connect these 2 models on the loss landscape. And this parameter T is the model index along the curve. And the theta is actually a parameter that you train, which has the same network architecture as the 2 end models. So you are basically training the theta to learn the optimal path along which the loss will remain constant. So the training loss is nothing but a function, the loss function is a function of theta. And when you evaluate the loss function, you basically sample uniformly on the curve function and evaluate the loss on the sample, the loss functions, and as your training function. And then you run stochastic optimization on the trusted data to update theta. That's how we are proposing to learn a path connecting 2 end models. So we will discuss how do we start from 1 potentially poison model to 2 poison models later. The picture on the right is an illustration of what that means. So basically, assuming we start with 2 potentially poison models, and then we want to find a better model in between. So these are 2 given models that are possibly poisoned. And this is the curve that we learned by optimizing this training loss. So after you learn this curve, you basically has the ability to select different models on the curve, and you can, it's fairly safe to assume the different models on the curve will have similar performance in terms of the generalization and test accuracy that's given by the mode connectivity analysis. So the goal here is really when we try to use the trusted data to learn this curve, how can we find a sanitized model that can alleviate the backdoor effect relative to the end model, but also making sure it still has good performance on the normal task. So here is some experimental results to validate what we are doing. We tested on several data and models, right? The models we use ResNet and also BGG. Dataset we use CVPR 10 and SVHN is a digital classification, codable digital classification task. And we also have some results on CVPR 10 100 in the paper. And we are considering the same backdoor attack. It's basically you have a fixed trigger pattern as shown on the figure on the right. With a fixed location, and then we consider not only a standard backdoor attack, we also consider adaptive attack that knows we are going to train a path to defend this backdoor attack. So you basically try to poison the whole path instead of poison the two end models. And to generate this so-called limited trusted data set, we basically divide the original test set into two subsets. The first subset is used to train the path, and the other subset is remained as an independent evaluation of the attack performance and also on the performance on the original task. And for backdoor attack, we consider two different types. So we can consider single target attack where the trigger is associated with the particular targeted class. And we can consider more sophisticated backdoor attack called the all target attack. It's basically the target label is the next label in a class index modulo the total number of classes. So if it's a if its original class label is 1, it will be classified as a 2 with a trigger, and 2 with a trigger will be classified as a 3, etc. And in our experiment, we add the trigger to 10% of the training data, which is a very typical setting. So the table on the right is basically to show how effective this backdoor model is. So we have two types of errors here. The first error is the standard error. That relates to the inverse of the standard accuracy. And we also have the notion of attack error, which basically means if the attack error is lower, that means the attack is more successful. So here, as you can see, the standard accuracy of a backdoor model is around 85 for CVPR and 95 for SVHN. So it's very similar to a normal model. And their attack error is very low, which means the attack is always almost successful. And similarly for this all target attack. So we can very easily successfully train a backdoor model without significant performance degradation on the normal data, but it still embeds this backdoor effect. So here is we try to illustrate how the number of limited clean data affects the accuracy on the path that we learned. So the summary here is that the use of limited clean data plus mode connectivity are actually sufficient to find a low loss path connecting two models in the loss landscape. So here we are showing two different things. The left is a training set, the right is a test set. And the different colors in this plot basically shows a different number of figures we are using to train a path. So as you can see, the more images we use to train a path, the lower the loss is on the loss landscape, because you have more information about when you do SGD to optimize the loss function. And we also have the two different types of curves here. So the solid line means the loss, cross entropy loss, and the dashed line means the cross entropy loss, and the solid line means the error rate, standard accuracy. So it basically shows a trade-off, right? The less data you have, the higher accuracy you are expected when you train the path, but they are still relatively well behaved. You can still get a reasonably good data on the path you learned with limited data. So this is the interesting part. So what we actually show is so how effective it is, right, with this idea to eliminate the backdoor effect. So it turns out this model connectivity provides a very good prior for trusted fine-tuning, right? So what we are showing here is the standard error versus the attack errors. Again, standard error is higher means the classification is worse, but the attack error is higher means the defense is stronger. That means the attack will be failed most of the time if the attack error is closer to 100%. So as we can see here, these two end models, t equals to 0 and t equals 1, they are actually poison models. And the models in between, right, there's a wide range of the good models out here where the attack are totally unsuccessful with 100% error rate, but the standard error rates are still quite low. So this is basically a very encouraging result for us to show with this trusted fine-tuning, with this idea of mode connectivity plus limited data for fine-tuning, you can actually recover a backdoor model, right? By making not backdoor, and also kind of remove the backdoor effect, but still keeps the performance on the normal task unchanged. We also benchmark our results with some other baselines, including fine-tuning. Just use whatever data you have to do fine-tuning, or you can do train from scratch, or you can do some weight pruning, right? Try to mitigate the backdoor effect plus fine-tuning. And you can also do add some Gaussian perturbation to the backdoor model weights. So the summary is none of the baselines really work. So train from scratch, right? It can completely remove backdoor because it is trained on clean data. But the problem is because we only have a limited clean data, the clean accuracy will be low. On the other hand, pruning seems to be very effective to remain high clean accuracy even with limited data. But on the other hand, the pruning is not able to remove the backdoor effect, so it still suffers a high attack success rate. The stronger baseline is actually fine-tuning, but we observed that for a different number of limited data sizes, fine-tuning is suboptimal relatively to our method. It performs really bad, especially when the data size is really limited. So here we basically compare different data sizes and the corresponding clean accuracy and backdoor accuracy and get the conclusion from there. And noisy perturbation with the randomness is basically didn't work at all. So we are able to conclude that our methods maintain the superior performance on clean data and at the same time can attain low attack accuracy, which is basically a very ideal solution. On the other hand, we also observed that the success of using mode connectivity is not by chance, because if you randomly find 1,000 different models around the backdoor model, they all perform very poorly. That means this mode connectivity is very crucial to provide the guidance to find a good model for sanitization given limited data size. As I alluded to earlier, we were focusing on the cases where we have two poison models. Now you may ask, what happens if I just give you one model? Are you able to do any fine-tuning and path connection? The simple answer is yes. So what we can do is we can separate the trusted data into two parts, and then we use the first part to train a fine-tuned model, and then we use the rest part to connect the fine-tuned model and the original model. And you can observe in our experiments that these results are very interesting in the sense that in some cases you can always find a better model in terms of a better, a lower standard error, and also removing the backdoor effect compared to the fine-tuned model. So this shows that our method actually is applicable even with given one trained model. We also have shown some results how to neutralize the models trained on different backdoor data sets. Here, the 2A models are trained with different fraction of poison data, and you can see we can still do a pretty good job in terms of recovering a poison model. Here, we also show some resilience to a path-aware attack. So you are poisoning the whole path instead of just poisoning two endpoints. But as long as you have a subset of clean trusted data, what we can show is that our method is still robust to this type of adaptive attack. In the interest of time, I think I need to move faster. So the other question that we often get is how do we select a proper model index T as the final return model for a sanitized model? So the answer is very easy. You can always set a tolerance on the test accuracy degradation if you can observe the test accuracy. If you only have a small set of clean trusted data, you can use a k-fold cross-validation to select the best model index T you have. We also do some extensions how to use this idea of a mode connection to evaluate robustness for evasion attack. So basically, what we observe is that if you use a standard training, right, backpath connection between three different pairs of models, right, including independently trained regular models, the pair of regular and adversarial trained model, and also independently trained adversarial trained models. In all cases, you don't observe any barrier between the models. But there exist robust loss barriers. That means loss evaluated on adversarial training when you involve adversarial trained models. So that basically is an indication of a no free lunch theory. It's not easy to find a better model in between two given models. So what we observe is that we can use this path connection analysis, and we can have some theory to show the largest eigenvalue of the model Hessian on the path is actually highly correlated with the robustness against evasion attack. In the interest of time, I will skip this slide. So the conclusion of our ongoing work is we basically have a very normal method for model sanitization. It works pretty well with limited trusted data by using the mode connectivity in neural nets. It's very effective against the standard and adaptive attack. It outperforms several baselines. And our ongoing work involves application of using mode connectivity to other topics within adversarial robustness. And we also have some works on detecting and explaining backdoor, how a model is backdoored or not, and try to understand the effect of data heterogeneity on federated learning setting. I also want to use last few minutes to discuss the idea of trusted AI. So robustness is one important dimension within IBM research, and we also care about other dimensions like fairness, explainability, and accountability. We have a rich set of representations published in the past few years covering attack, defense, evaluation, certification, and interpretability jointly with our academic partners. So actually some of the invited speakers here are actually our academic collaborators as well. We also released an open source toolkit called the Adversarial Robustness Toolbox for researchers interested in this dimension to explore further how do we make the model robust and properly benchmark robustness. Finally, I would like to do a shameless advertisement. So if you are curious to learn more about our research, I will be given a tutorial at the ECCV 2020, also online version. And we already give a tutorial on zeroth order optimization, which is a fundamental tool for zeroth order optimization and black box models. It's already given at CVPR, and we plan to release the model on YouTube pretty soon. With that, I will end my talk. Thank you.
Thanks, Ping, for your great talk. We then move to the next speaker. Our next speaker is Chu Hui Xie. Professor Chu Hui Xie is an assistant professor in UCL's CS department. His research focuses on efficiency and robustness of machine learning systems. Chu Hui obtained his PhD from University of Texas at Austin in 2015. He is the recipient of the IBM PhD Fellowship, the Best Paper Award in KDD 2010, ICDM 2012, ICPP 2018, and the Best Paper Finalist in ARSEC 2017. Yeah, you can begin your talk. Thanks.
Okay, thank you for introducing me. Yeah, so can you all see my screen?
Yeah, you're fine here. Yeah.
Yeah, thank you for inviting me. So I really enjoy this workshop. There are very diverse topics on the talks, and I hope my talk will add some more diversity to this workshop. So instead of talking about neural network, today I will focusing on, so part of the talk will be focusing on other machine learning models, including decision tree and nearest neighbor classifiers. Okay, so people have been studying the adversarial robustness of neural network for maybe more than 5 years, and we all know neural networks are not robust to small perturbation, and people come up with many different ways to try to improve the robustness and try to measure the robustness of neural networks. So, however, given there are lots of work on neural network, there are actually very few work on discussing the robustness of other machine learning models. So today I'm going to focus on two other machine learning models. One is the tree ensemble model. So this includes gradient boosting tree, such as XGBoost, and also random forest models. So the tree ensemble model, although they may be not as powerful as neural network in like ImageNet classification, but they are actually the best model for many Kaggle competitions, and many practical data sets are actually using the tree ensemble models. And also I will talk about the nearest neighbor classifiers. So this is one of the most traditional classifier, and I think people still using it in few areas, especially when you combine this with the metric learning. If you learn a good metric instead of using Euclidean distance, then this can still be very useful. And also we start to doing some work on nearest neighbor classifier because many people are using this for the defense, including the Lawrence talk, like before Pingyu's talk. So we're trying to, so this is actually one of the motivation. When people use nearest neighbor classifiers for defense, how do we analyze the robustness of such models? So before going to the detail, I will try to give the brief overview of how to measure the robustness of the machine learning model. So here is the illustrated example. So the middle point is the black point here is the original example, is a natural example, and we have the blue decision boundary like this. So everything within the decision boundary will be classified correctly, and outside the decision boundary will be classified wrongly. So the definition of adversarial robustness can be mathematically defined as the shortest distance to the decision boundary. So it will be the radius of this red circle, and you can guarantee within this ball with radius r, there is no adversarial perturbation can exist in this safe region. And this is also the minimum distortion you need to perturb the data to another class. So in practice, it's usually hard to compute this min-mount. We call this min-mount adversarial perturbation. So this is just the shortest distance to the boundary. So in practice, it's usually hard to compute this r, the red number r in practice. For example, it's NP complete for many problems, including ReLU network. So what people can do is you use the attack algorithm to find the adversarial example outside the decision boundary. So this is like the green start in this picture. So we can see this will give you the upper bound of your minimal adversarial perturbation. And on the other hand, you can also try to find the lower bound of this minimal adversarial perturbation. So this is a class of algorithm for neural network verification. So you try to find a safe region where no adversarial perturbation can exist within the radius r prime. But this is not optimal because this is smaller than the red circle. So this is equivalent to finding the lower bound of r. So I think many of the problem when we analyze the adversarial robustness of neural network happen because you cannot really compute the exact minimal adversarial perturbation. So even if you do the attack, like you do a CNW or PD attack, you get the adversarial example like a green example, but you don't know whether this is the best adversarial example or this is just a very large upper bound. And in neural network, actually, the ratio between this lower bound and upper bound can be often larger than 10 or even larger than 100 when you go to a very huge network like ResNet. So some of my students are actually trying to do the neural network verification to compute lower bound. So you can compute this ratio based on our software. But so later on, we will see in when I talk about the nearest neighbor classifier and the tree ensemble classifier, we'll see much smaller ratio between these two numbers, which means we can much more accurate measure the robustness of those models. Okay, so this is the roadmap of today's talk. I will first talk about the decision-based attack. So this is kind of related to neural network because the decision-based attack is like a universal way to attack any decision-based model, including neural network and discrete models. And then I will talk about how do you more accurately measure the robustness of k-nearest neighbor and the tree ensemble. Okay, so decision-based attack, this is joint work with my student Ming Hao and also Ping Yu in the previous talk. Yeah. So in the decision-based attack, what we're trying to do is we assume your model is a black box, and what the attacker can do is to send a query to the black box, and the black box will give you the prediction label. So you input X and you observe the prediction label, but you don't get the you don't know the probability of the prediction. So many existing work doesn't attack doesn't cannot work in this case. So we call this the universal way to attack the machine learning model, because the black box, we only require the black box model to give us the prediction class. So even for a decision tree or for new security point of view, this is also the most realistic setting of the attack. So the attacker doesn't know anything about the model. Okay. So why this is very hard in practice? So usually for example, in CNW or PGD attack, we're trying to solve an optimization problem to find the adversarial perturbation. So assume X0 is your original example. You want to find the adversarial example X by minimizing this function. So the first term is the distance between the adversarial example and the original example. You want to minimize this. And you want to use the loss function to measure the successfulness of the attack. So the loss function, for example, in CNW, you use the difference of the logic layer output to measure the successfulness. In PGD, you use the cross entropy loss. So these are good for white box setting. But when we come to the decision-based black box setting, what happened is your L of X is actually a very non-smooth function. So because you only know the prediction class of your classifier, you don't know any probability output. So your prediction is either correct or incorrect. And L of X defined on this binary prediction will become the step function like the third plot here, the plus C here. So there is no optimization algorithm can be used to optimizing this kind of function. So instead of using the original formulation, we try to reformulate the decision-based attack. So this is the work in ICOR 2019. So what we're doing is in our reformulation, we try, instead of finding the adversarial perturbation, we try to find the direction of the adversarial example. So we define theta to be the direction of the adversarial example. And for every theta, we define a distance, or we define the function g of theta to be the distance from x0 to the boundary along this theta direction. So for example, if theta 1 is this direction, then the g of theta 1 is the distance between x0 and this point on the decision boundary. So given any theta, you can define the distance to the decision boundary. And what you want to do is to find the optimal theta to minimize this g of theta function. Okay. So this is in the on-target attack, but in targeted attack, you can define using other ways similarly. So once you define this function, so from this figure, you can observe if your theta change a little bit, your g of theta actually only change a little bit. So this is usually a smooth function as long as your decision boundary is not very weird. So you can see in neural network, this function is actually a smooth function, and also for decision tree ensemble is also a smooth function. And the main problem of this, so this sounds like very good, right? You define some function you want to minimize, and the function is somehow smooth. So you can use gradient-based optimizer to optimize those functions. So what's the difficulty here is you cannot really compute the gradient of this function. Actually, you cannot accurately compute the function value of this. There is no closed form. So what we're going to do is we try to run some zero-order optimization algorithm. So instead of computing a gradient, we try to estimate a gradient. And to estimate a gradient, you need to compute the function value of g of between theta 1. So you need to compute difference of G theta 1 and G theta 2 when theta 1 and theta 2 are very close. And in order to compute this function value, in the 2019 paper, we proposed to use a fine-grained search plus binary search. So I will not give the detail here, but it's somehow like you are given the direction. So you try to divide this direction into many different blocks, and you try to find the first block that is outside the decision boundary, and then you do the binary search within such region to find the accurate value of G. So the zero-order optimization algorithm will look like this. So every time you random sample some direction, some Gaussian random variable, and then you try to evaluate the difference between G theta and G theta plus some small beta times this direction. So it's like you try to use the difference between G theta and G theta plus beta u to estimate your gradient. So this is like a finite difference estimation of the gradient times the direction vector. And imagine if you take an expectation of this term, then it will become your equal to the gradient. And then so G hat is like a stochastic estimation of the gradient, and then you update your theta by this step size times G. So this algorithm is actually working well. So it's better than some non-optimization based algorithm like previous boundary attack. But there is a problem that you require a lot of queries in this step. So in the second step, you want to evaluate the G theta and G theta plus beta u. And as I mentioned in the previous slide, for every function evaluation, you need to run at least a binary search to get the value. So for each of these, you need like 10 queries. So totally, you need like 20 queries for this step. So the question is, can I further reduce this 20 queries in like every for loop? So in our iClear paper this year, we actually just modify this line to reduce the query. So the main idea here is instead of using so here you try to estimate so you know the direction, and you try to estimate the magnitude of the gradient very accurately. But now we're in a stochastic setting, so maybe the magnitude of the gradient is not so important. Only the sign of the gradient can already give you sufficient information to do the update. So what we are doing is we replace this thing by the sign of the finite difference times the direction u. So instead of computing this magnitude, I only compute the sign of this thing. And then because the sign of G theta plus beta u minus G theta by beta is equal to the sign of these two so it's equal to sign of the G theta plus beta u minus G of theta t. So this means you only need to know between these two directions, theta t and theta t plus beta u, which one is closer to the decision boundary. So in order to compute this, actually you only need one decision-based query. So if you know the current value of G theta, then you can just test if you go with this magnitude on the direction of theta plus epsilon u, whether this point, so it's like you have this line and you rotate to the new direction theta plus epsilon u, and you try to check whether this point after the rotation is inside or outside the boundary. If this is outside the boundary, then this means the real distance G theta is smaller than the original one. So it will be -1. The sign will be -1. Otherwise, it will be +1. So this is the exact computation of the sign of this term, and this only requires one single query in the decision-based model. So using this, you can reduce this to one query from 20 queries, so you get a lot of speed up. And you can observe here, we compare our sign OPT attack with previous attack, and we can get much more better L2 distortion with smaller query. So I know there are still many recent work on trying to improve this. So one thing is we still need like more than 10,000 queries for InfiniNet. So there are many recent papers trying to using better distribution, sampling distribution to further improve the query counts for this algorithm. So now I'll go to our main topic here. So I want to use this to measure the robustness of a discrete model like a gradient boosting decision tree. So what's the difference between the boundary of GBDT and the boundary of neural network? So here is the comparison. So you can see the boundary of neural network, although there may be some local optimal, so this is the red line are connecting from x0 to the local minima on the decision boundary. So you can see the boundary of neural network is relatively smooth, while the boundary of the GBDT is actually very sketchy. So there are many different local minima on the decision boundary of GBDT. So it's the similar thing for the nearest neighbor model if you have many samples. So if you use the decision-based attack to attack those two models, for neural network, you can see when you use random initialization, the variance of your final solution is between 1.35 to like 1.5. But if you use decision-based attack to attack GBDT, then the variance, then the solution can vary from 1.0 to like 2.3 or 2.4. So it's like so this is because there are so many local minima on the boundary. So you need to do a lot of random initialization to attack those models. So in the recent paper, we try to use multiple restart plus successive halving to do the attack on like those models. And but I will skip the detail here. But basically, this kind of decision boundary, decision-based attack can give you some rough idea of what's the robustness of your model, but it cannot give you the correct estimation of this because it's a very large upper bound and the variance is very large, so it's not very reliable from my point of view. So the next topic I will talk is the robustness of nearest neighbor classifier. So here I will show we can actually exactly measure the robustness of nearest neighbor classifier, and we can also do robust training based on that. Okay. So the nearest neighbor classifier is its notation. So we have the original example is like a star, and you have a data set. So some points are in class A, some points are in class B. You take the k nearest neighbor, you try to do a majority voting, and then you decide the output label. So as I mentioned, we want to compute the minimum distance from the original sample to the decision boundary of the k nearest neighbor classifier. So I use epsilon star to denote this distance here. So let's try to do some simple example. This is what I did when I started to do this research. So assume Z is your original example, and you have two samples. This is the circle is the positive sample, and the triangle is the negative sample. So you want to move your Z to the negative sample. So what's the shortest distance to make KNN predict the negative? The shortest distance is actually the distance to the bisection of these two examples. So epsilon star is this when there are only two samples. So when there are three samples, you can see there are two circles and one triangle. In this case, the optimal the minimal distortion to perturb it to the negative prediction will be this blue, the epsilon star here. So you can see this is not the projection to the bisection, but this is the distance to the intersection of some bisection. So mathematically, in the geometry, this is called a corner. So when you have a KNN classifier, you can plot a lot of bisections. So for every 2 points, there will be a bisection, and the intersection of bisection will be a corner. So in order to enumerate the smallest perturbation distance to the negative class, you need to construct all the corners in this nearest neighbor classifier decision boundary, and then you try to test each of them. So in geometry, this is called a Voronoi graph. So each cell is the region which will be predicted by this the class of this sample. Also, here we only consider the one nearest neighbor classifier. In the k nearest neighbor classifier, this is we'll use a higher order Voronoi graph. So in this case, Voronoi graph construction is usually NP complete for very general D. So only for 2D you have a polynomial time algorithm. So it's like we think maybe can is polynomial kernel robustness cannot be computed in polynomial time. Maybe it's NP complete. But surprisingly, after a few weeks, we found there is a very efficient polynomial time algorithm for computing the robustness of one nearest neighbor classifier. And the algorithm is actually very simple. So in this formulation, I try to, so Z is my original example. And I try to make it, I try to ask the question, what's the smallest perturbation to make Z closest to target example Xj? So the formulation here is I want to find the minimal perturbation delta such that the distance between Z plus delta minus Xj is less or equal to the distance between this sample and all the other samples. So the condition ensure Xj is the nearest neighbor of Z plus delta. And we want to minimize the norm of delta. So by this way, epsilon J will be the smallest perturbation you need to perturb your Z to be closest to Xj. And this looks like a hard problem, but actually after simplify it, you'll see it's equivalent to a quadratic problem with linear constraint because the square term here will cancel out. So it becomes a linear constraint. And this can be solved in polynomial time because it's just a simple quadratic problem, programming problem. So in order to compute the minimal adversarial perturbation, we have a very simple algorithm. So you try to construct a set all the negative samples, and you try to compute the shortest perturbation in order to make it closest to each negative sample in this set S. And then you take a minimal, which will be the minimal adversarial perturbation. So this is a polynomial time because every of these epsilon J computation will be polynomial time. However, this is still slow in practice because you have a lot of quadratic programming problem to solve. For every negative sample, you need to solve a quadratic programming problem. And for every quadratic programming problem, you have D variables and N constraint, which require a lot of time. So if you use the best commercial solver, like this is the best one we found by Stephen Boyd. So this will, if you want to verify one set, compute the minimal adversarial perturbation for one example, you need more than 20 days to do this on MNIST dataset. So what we're going to, we're going to transform this problem to a dual problem. This will give us the holistic view of the attack and defense in the nearest neighbor classifier. So let's say the P of J is the primal problem, quadratic problem I mentioned to compute the epsilon J, the shortest distance to perturb to some particular example. And the dual problem will be some, so you transform the constraint to the objective function and objective function to a constraint. So the dual problem of this will become another quadratic programming problem. And from the dual identity, we know the optimal solution of the primal will be equal to the optimal solution of the dual. And you take a mean over all the negative sample set. So this is based on the convexity of the objective function. So you know both of these, the optimal of primal and optimal of dual will be equal to the minimal adversarial perturbation you want to find. So if you don't want to compute this exactly, what you can do is to find the upper bound or lower bound of this value. So to find the lower bound of the dual problem, you can just, instead of using the optimal dual solution, lambda star, you can replace this lambda star by any feasible dual solution lambda j. So any feasible solution, trivial solution can give you a lower bound of this thing. And this can be used for verification. And on the other hand, for the upper bound, you can try to solve a subset of this primal problem. Instead of going through all the negative sample set, you can just go through a subset of negative samples. So intuitively, you can start from the naked sample, which is close to your current sample, and then do it sorting by the distance, and then do it one by one. So this will give you a pretty good upper bound for this. Okay. So for the verification, as I mentioned, any dual solution, feasible dual solution will give you a verification. So in our paper, we try to use the most simple one is the lambda equal to 0, 0, 0 to 0. So all zero solution. So, but this will give you a non-meaningful solution. So we try to allow it to have one coordinate equal to non-zero. So this is like taking the 0 and then updating one of the element to the non-zero in the dual space. So this will give you a lower bound like this, which can be computed efficiently. So in this lower bound, you just need to evaluate all the negative sample and positive sample, and then compute this distance in constant time. So, and this can be generalized to k nearest neighbor case. If you are in the k nearest neighbor case, then you just compute the k smallest and k largest one, then you get the KNN verification algorithm. So I'll skip this. So in our paper, we also show how to efficiently compute the exact solution, minimum adversarial perturbation of the nearest neighbor classifier. So we are using the screening rules to solving those QPs. So the intuitive is some of the quadratic programming problem, they are more important if, for example, for this triangle, which are very close to your original sample, this is more important than another example, which is far away. So using some primal dual relationship, you can actually remove some of this theoretically. And this will not change the final solution. And also you will derive the screening rule for the reducing number of variables in the QP. But this doesn't work for k larger than 1. So for k equal to 1, we have an efficient algorithm to compute the exact epsilon star. But for k larger than 1, we can only do the verification to get the lower bound of it. So this is the result on one nearest neighbor classifier. So you can see for MNIST, this is the exact L2 perturbation to make it adversarial, to change the class. And the verifier will give a lower bound, and the attack will give an upper bound. So you can see our bound is much better than previous bound using some other naive attack algorithms. And also the computation time is pretty similar for all these algorithms. Okay, so we can also extend to the 15 NN case for the verification algorithm. And the main thing I want to show, I think in the last minute, is the comparison between the nearest neighbor classifier and the neural network. So actually, as we show here, the nearest neighbor classifier, the exact number and the verifier and the attack will give almost similar perturbation number, which means those numbers are very tight. But for neural network, as I mentioned, the verification will give very loose bound. So we can see if we compare this one nearest neighbor classifier with the state-of-the-art certified defense algorithm by random smoothing, then the blue curve is the one nearest neighbor, the red curve is the certified defense in neural network. And it's actually much better than the certified defense in neural network for MNIST and fetching MNIST data sets. So we are not claiming KNN can be used to replace neural network, but at least for some small data sets, it can be very useful if you really want a robust classifier. So we also try to derive the algorithm for finding the metric which is robust. So by using our verification bound, you can get the epsilon, and you can try to optimize the objective to maximize this epsilon to find the best Mahalanobis distance for the nearest neighbor classifier. So by solving, so I will not go into detail, but by solving this, you can further improve your robustness of KNN by a small margin like this, the blue curve versus the red curve on MNIST and fetching MNIST. So I'll skip through the decision tree part. If you are interested, you can send me email and we can discuss later on. So in conclusion, we talk about decision-based attack, which is a universal way to evaluate the robustness of many different machine learning models. And currently, there are still many challenges in this, including large number of queries And as I mentioned, they are sensitive to initialization. And we are not sure how to use. So if our goal is not the security goal, if our goal is to measure the robustness of a particular model, then how do we use some prior knowledge of this model to improve the decision-based attack? For example, if I want to use decision-based attack to attack a tree-based model or KNN model, how do I improve this according to what model I want to attack? And also for the rest of robustness of KNN, we talk about exact verification of one nearest neighbor classifier. But the k nearest neighbor classifier when k larger than 1 is still an unsolved problem. So we don't know whether it's NP complete or not. It will be interesting to have this kind of result. And also our metric learning algorithm is focused on linear Mahalanobis distance, but there are many other metric learning on nonlinear metric, which may be even improving the robustness. And then our final goal is to evaluate the robustness of KNN plus neural network model, something like the Lawrence work or some previous work by Papernaut. But currently, we're still looking for how to combine this analysis with a neural network to get a final certified defense algorithm. Okay, so this is my talk. Thank you very much.
Yeah, thanks, Professor Xie, for your great talk.
Yeah, thank you. I'll mute myself.
Yeah. Yeah, then our next speaker is Dr. Bo-Chin Gong. So he's a research scientist at Google Seattle and a remote principal investigator at ICSI Berkeley. His research in machine learning and computer vision focuses on modeling, algorithms, and visual recognition. Before joining Google in 2019, he worked in Tencent and was a tenure-track assistant professor at the University of Central Florida. He received his PhD in 2015 at the University of Southern California. So the talk title is Towards Visual Recognition in the Wild, Long-Tailed Sources and Open Compound Targets. So let's welcome Bo-Chin Gong for his talk.
Thank you, Xinyin, for the introduction, and thank all the organizers for having me here. I also want to say hi to all the old friends and new friends in this workshop. It's great to see you. Okay, yeah, so I'm in Google Seattle. It's too bad that this year CVPR, which was supposed to be here in Seattle, but it cannot come here. So here I want to show you one picture I took last year. It's a beautiful view. So in the future, if you come to Seattle, welcome to drop me an email. I would be more than happy to host you in Google. So my talk will be mostly two parts. So long-tailed sources and open compound targets. So before reaching what I mean by those, I want to start it with this paper. It's about object recognition, published about 11 years ago now. So at that time, I was actually still a junior graduate student. I tried to decide what I want to study in the graduate school. So in computer vision, you can go with like a low-level vision, like a computer vision plus computer graphics, that path. You can also go with the computer vision plus machine learning, this path. I read this paper, it became one of my favorite papers at that moment. So it has a nice graphic model here to show then how to use attributes to recognize objects, even if you haven't seen them before. I have about 50 classes in their paper. I really love this combination, very neat combination between machine learning and computer vision. So I started to apply to graduate school and started to do a PhD in machine learning. I worked on domain adaptation. So you have basically different type of data, different type of distribution. The goal is always to get a good performance for your model on the target domain. At that time, of course, all the techniques mostly are on kernel methods before deep learning. And experiments, I still use computer vision models and computer vision datasets. We play with sometimes about 100 classes, and we are pretty happy with that. I published one paper in CVPR, but all the others are on NeurIPS, SML, on the machine learning conferences. Well, I was partially being away from the community, actually there's a lot of fantastic things happening. One, of course, is the ImageNet challenge. Right now we can, let me try to get the pointer. We can get even superhuman performance here, and you can see. And also we have a lot of classes, about 1,000 classes. This is kind of like the Pandora box in a good sense, And to me, this paper opened this Pandora box because I was working on a lot of computer vision datasets. And what this paper showed is that even if you do not apply the neural networks, even if you only use deep features, you can already beat all the existing state-of-the-art results at that moment. This is a paper in 2014. And of course, very quickly, people started to do the fine-tuning or transfer learning from ImageNet to all different computer vision tasks. Okay, so also it's about, and then time I graduated from my PhD program, become an independent PI. So I wondered, it's time actually to don't indulge myself or my students in like just the established data sets in the community. Don't be happy with only like 100 of classes. Let's go wild. Let's see, okay, so we got a really unprecedented performance in a lot of data sets, what we can do in the wild. One of the most, to me, I feel one of the most kind of challenging data sets, which really well represents the real world, is the iNaturalist dataset. It's a dataset collected by Google together in partnership with an institute in California. They have a lot of biologic scientists, and they contributed a lot of data in the wild. Also, for every single image, they have annotations, not from the crowdsourcing kind of like AWS workers, but actually by scientists. Also, there are a lot of classes. So we started to look into this dataset. And very interestingly, because the data is from the wild, from the real world, you have a very long-tailed distribution over the classes. Some of the classes actually have only 5 or 10 training images, but the others, you really got up to more than 1,000 training images. So how can we still apply previously successful machine learning techniques in the standard manually compiled datasets to this is a little bit more wild dataset? That's become the problem. We tried different techniques, and then this long-tailed distribution, however, is always kind of like the challenge there. Then we started to look around to see whether this phenomena is only unique by this dataset, or actually it's, let me try to move this. It's popular in other datasets in the wild. The answer is yes. If you go to the real world datasets, some datasets I meant that it's not manually compiled, manually pruned. You always have this long-tail distribution. So here I give you 4 more examples. This one is from the scene understanding dataset. So it's compiled for scene understanding. It's balanced across different places, different scenes. However, if we check the objects in this dataset, they are long-tailed because we never tried to manually tune the distribution of the objects. Second example is Flickr. If you check the Flickr tags, they also follow a long-tailed distribution. This is a landmark recognition dataset, and you can see we got a lot of training images from North America, from Europe, and East Asia. But the other areas of the globe, it's unfortunate that we don't have a lot of training data. Probably you are more familiar, I think the audience in this workshop, more familiar with this one. It's called a large-scale instance segmentation dataset from Facebook. Also, it has a long-tailed distribution. Okay, so given all of those, I hope I have already convinced you. I hope you are with me that it's not something that this long-tailed challenge in visual recognition, it's not one particular phenomena for one dataset or one task is really there for all different tasks and the data sets in computer vision. In the future, if we really want to push the boundary of visual recognition further, we have to deal with this challenge. So we therefore formalized this problem in 2018. Of course, the paper came out in 2019. So in 2018, we felt it's the time to actually formalize this problem to become an independent research problem we want to study. So previously, they have appeared in some papers and like a small section or some modules in some of their approaches. We feel, okay, it's actually time to make it independent, and we should try to study it, try to solve this problem by formalizing a research problem. So we compiled 3 long-tailed distribution data sets with long-tailed distribution over classes. So here about 1,000 classes, here about 3,000 classes. We also got a phase data set. Okay, so the idea is don't want to go really with a lot of classes because otherwise maybe some research labs might be struggling to play with the data set. So we try to find a balance between the scale and the long-tailed distribution. Hopefully that researchers from academia and industry, they can all work on this problem. Also, we got I think, straightforward a neural architecture at that moment, which is to use the memory bank to enhance the tail classes. So we got good results. And then I joined Google. We started to kind of like argue with one of my great colleagues, Matthew Brown, regarding what's the difference between this long-tailed recognition and the traditional imbalanced classification. Then we can sort of concluded that these two are kind of like interesting mix of the old AI and the new AI. By the old AI, I mean the imbalanced classification. The people, we have been working on this problem even before the deep learning for a long time in different communities, in machine learning, computer vision, data mining. But now, because of the tail, we really actually got a few-shot learning problem for the tail classes. And if you check the existing approaches to few-shot learning, we got meta-learning, we got transfer learning, zero-shot learning. So different techniques. So this problem, this long-tailed recognition problem is really a natural blender or mix of these two different problems. So hopefully, therefore, we can also motivate a lot of new techniques as well. Then it's a little bit unfortunate because if we check the recent publications, they all reported very good results, but they mostly try to weigh different classes. So the class or the instance weighting is really kind of like the cornerstone in domain adaptation. So I therefore went back to the old equations in domain adaptation, which I studied during my PhD program, tried to understand this long-tailed recognition from a domain adaptation perspective. So we got a long-tailed training set. Of course, the tail here is over classes. But we don't want the model to be unbiased. We want the model to be high quality, high performing, actually over all classes. So in other words, we expect balanced or roughly balanced testing set for the model. If we formalize this problem a little bit more carefully, so, and you can see the equation here, of course, still, as I said earlier, very cornerstone, but very old equations in domain adaptation. So nothing fancy. You can see here, we want to have good performance on the target. In the long-tailed recognition scenario, we want the model to perform well on all classes. So this target, therefore, is unbiased over classes. We don't know the testing data, of course. We can change the distribution by the trick in importance sampling. So we sample instead from the long-tailed source domain. And of course, you need a weight here. If we decompose them into a marginal over a class, here PS is the source. We know it's long-tailed. PTY is the target. We know we expect it to be roughly balanced, because we don't want the model to be biased to any of the classes. We want it to perform well over all classes. So we use a roughly balanced testing set to test the model. Also, we got conditional distributions here. And further, we wrote them into some omega y and 1 plus states for this part. And you can see, by trying to weigh different terms in the training over classes, these approaches, they are effectively assuming that epsilon is 0. In other words, let me show this figure, maybe it's more clear. In other words, they're assuming that the two conditional distributions between the source and the target actually are the same. I don't think that's the case. Let's try to study these two distributions a little bit more carefully. So in the head classes, given a class cat, the conditional distribution probably can be well represented by a lot of training images, because you have a lot of training images in a training set. Maybe it's okay. But for the tail classes, given a class tag, for example, it's really hard to get enough training images to well represent this tail class. So it's really hard, therefore, to assume these two are the same. So we tried, therefore, challenge the existing assumptions in existing works, and we formalized them into some, I think, very straightforward equations in the paper. It's well received in the community. And we tried to argue that long-tailed recognition actually can be understood from the domain adaptation perspective. Of course, in the paper, we also tried to estimate not only the class-wise weights, but also the weights for every example, so the epsilon. By a meta-learning approach, so naturally connecting the kind of old AI problem, estimating class-wise weights, and the new AI problem, which is to use meta-learning to improve the few-shot learning scenario. We got state-of-the-art results on 6 datasets. I will skip the results. Instead, I want to emphasize by this slide that by understanding this problem from the domain adaptation perspective, is really, I hope, is really helpful for the future work, because domain adaptation, it has been there for many, many years. And we have some very successful techniques, maybe not successful, you can call it at least popular, popular techniques, like learning domain invariant features, curriculum learning, adversarial training, class discrepancy, a lot of data synthesis and data augmentation techniques. So we hope these can benefit the future work to the long-tailed visual recognition. Okay, okay, I will skip this. So that's one challenge when we tried to extend the visual recognition to the real world. And meanwhile, I want to touch on the second aspect, which is the adversarial attack and adversarial defense. I honest with all the audience in this workshop, I feel the adversarial kind of robustness is definitely what we need, but probably it's not there yet, because adversarial attack, maybe it's a real risk for the visual recognition models, maybe not, we don't know yet. But at least we try to build up some robust models to prepare for the worst case. But of course, in order to do the visual recognition model, which is robust, we need to know the strong attack in order to do the defense, right? So in 2018, this paper came out. They tried to see that, okay, all the existing defense models are not really not good enough. So they can break those models, 7 defense models, by white box attack. So it's very natural, therefore, to ask, what about blank box attack? Could you actually successfully break the state-of-the-art defense models by some blank box attack algorithms? And that time, I was working on reinforcement learning. So it's very natural, therefore, to consider blank box as kind of like an environment. We don't know the gradients. We cannot pass the gradients through that blank box neural network. But we do know in reinforcement learning, policy gradient descent, it's very natural solution to that issue, right? So we tried to apply this policy gradient descent basically to this black box attack. We consider this as the environment, and our policy is the distribution over the adversarial examples. So more concretely, given an input here, we try to impose policy distribution over this input, such that the policy will try to propose adversarial example. So in other words, if these are the adversarial examples, they will have really high density in the distribution or in the policy here path. So it's very straightforward actually to learn this path. We want to maximize the cross-entropy loss. Basically the traditional classification loss, we try to minimize it to learn the neural network. Now instead we want to fool the neural network. Therefore we try to maximize the network with respect to this policy, which is the distribution, right? I give you a little bit more detail here how we specify this distribution. It started with a Gaussian, similar to the traditional generative models like a variational encoder or some generative adversarial networks. Therefore, that's why also we name this attack algorithm as Gaussian attack. The results are surprising. It's better than we expected. We tested about 13 state-of-the-art defense algorithms published at that time on both ImageNet and C410. And you can see we really got a very good success rate. So we can successfully attack almost all of them, except some other strong, some models of course are very strong. So we can partially hear about 40% of the success rate, but still very good. You don't want to deploy a model which has only 40% accuracy in the real world. Okay, so it's also, yeah, for the time being, I want to speed up a little bit. Please try to, be with me. It's also because of the reinforcement learning I was working on at that moment. So one of my former students, Yang Zhang, he got very familiar with the simulators. Then we tried to do something with the simulators. Therefore, can we actually try to generate some physical camouflage to hide some vehicles from neural detectors? And you can see here, when the color changes, it means we failed the neural network a little bit. So the answer, therefore, is yes. After indulging ourselves on the attack side, we really don't want to work on the attack side anymore. I think we have a common sense in this community. It's way easier to do attack than doing defense. Therefore, let's try to do the hard problem now. So it was perfect timing when we started to consider this problem, because I moved to Google, and Cihang, one of our organizers, also moved to Google. We also got a lot of nice infra inside Google. So naturally, we started to think, can we try to build a robust neural network by neural architecture search? So all the existing models, neural network, we know they are not very robust. Can we therefore try to design a new search space, maybe try to search a different neural network? Maybe it will be more robust than the existing neural networks. We started to work on this, and Cihang is really, really great. So he successfully published not one, but two very good high quality publications. This is one in CVPR 2020, and another one we submitted to NeurIPS. So I will actually have to skip this one because it's under submission and review. But the whole idea is to do the search by a little bit neural architecture search, and plus a little bit manual tuning to get a more robust neural network. Okay. So these two, the long tail distribution and the adversarial attack defense, are maybe two challenges we can identify when we try to use machine learning models, computer vision, visual recognition models in the wild. The very last one is domain adaptation. So it's always the case that I want to extend the visual recognition model to the wild. See, okay, if we do that, what are the main challenges? then we come back to the research lab or to the company, then started to work on that. So the very last aspect I want to share with you is domain adaptation. I will try to ramp it up in 2 minutes. Okay, so let me use self-driving as an example. Almost all self-driving companies, they have their own simulator. Here, simulator is not necessarily the computer graphics. It could be real scenario. They can, for example, buy a large area and then they drive the car on that area, in that area, and then they can try to simulate all different physical scenarios in that area, right? So they try to get all the possible scenarios on the testing stage, like different weather conditions here. But no matter what they do, I hope you agree with me, there are some cases, some scenarios that the training set really cannot cover. Not only that case, it's also that even if they cover all the scenarios in their training set, maybe they do not have enough training data to well represent some of the domains here, some of the weather conditions. Therefore, we tried to formalize this scenario into a research problem. We call it an open compound domain adaptation. The setup is the following. So we have a large-scale training set. It tries to cover a variety of scenarios. And meanwhile, we got some unable data from a lot of different scenarios. We don't know from which scenario those testing data are from, those unlabeled data are from, but we do know they have a very different and heterogeneous testing scenarios. We call them domains. And in testing stage, however, we want to test the model on all the scenarios, not only in the training stage scenarios of the training set, also the domains of the compound here in target domain, as well as some open domain, which means we do not have any data, no matter labeled or unlabeled, from this domain, but we want the model to perform well on this domain. So given time, I will only introduce this problem to you, and I have to actually skip this technique. You can try to reach out to me after this talk. Instead, let me try to summarize. So I like the research methodology that we try to not only actually work on the well-established data sets in the community, but also try to think of what happens if we want to apply what we have in the community to the real world. We got all different challenges, like a long-tailed distribution, like a domain adaptation, like the adversarial attack. So after identify those challenges, we can come back to the research lab and then try to formalize those challenges into research problems. The long-tailed recognition, we could use a memory bank to enhance the tail classes. And by understanding this problem from domain adaptation, I hope you agree that actually we could benefit from the really rich set of techniques in domain adaptation to develop better models for the long-tailed recognition. Of course, also, I want to share that the long-tailed training set is a nice mix of the old AI, which is the imbalanced classification, and the new AI, which is the few shot or meta-learning problems. How to mix these two, how to develop better advanced techniques from these two different areas would be also very interesting. Domain adaptation, okay, I will skip this. It's a really rich subfield as well. I want to, yes, so end this talk by this page. We do want to get good models. I will probably not work on attack anymore. Instead, I will try to work on defense. So all the existing approaches, they try to do like a data augmentation. I consider adversarial training as also a type of data augmentation as well, or data cleaning, randomization, quantization of the networks, including weights and activations. Those are all good. What's missing is the architecture. Actually, we already know existing architectures are not robust. Can we try to do like some Lipschitz continuous network or large margin networks? We know they are certified robust, but can we improve their accuracy? Or can we use some existing other modules, try to build up memory banks or stateful modules or denoising modules into the network to improve their robustness? Those are all good questions, I think, to need to be answered. I would be more than happy to see if in the field we can come up with some solutions in the future. So I will stop here. Thank you so much. We can discuss more in the panel discussion.
Okay, great. Thanks, Boxing, for our talk. Our next speaker is Thomas Dietrich. Dr. Dietrich is a professor emeritus in the School of Electrical Engineering and Computer Science at Oregon State University, where he joined the faculty in 1985. Professor Dietrich is one of the pioneers of the field of machine learning and has authored more than 190 publications and 2 books. His research is motivated by challenging real-world problems with a special focus on robust artificial intelligence and substantial development. He is best known his work on ensemble models in machine learning, including the development of error correcting output coding. Dr. Dietrich has a long record of service to AI/ML community, including the president of AAAI, president of the IMLS, and the executive editor of Machine Learning. Yeah, you can begin your talk.
Well, hello, everyone. So if we were face to face, I would be encouraging everyone to stand up and stretch for a moment, which I just did, because this is, wow, basically 2.5 hours of continuous detailed information. I also wanted to comment on how really excellent I found the other presentations. You know, when I was considering what to present here, I felt like there was a trade-off between doing something more on the big picture, and I thought Alan Ewell's talk this morning was really wonderful in that regard. And I share his sense that that we are maybe moving beyond statistical learning in terms of the tools we need to build good computer vision or good AI in general. That we were starting to encounter some of the challenges with statistical learning, not the statistics by themselves, we're not able to get enough data to really exercise all of the modes of variation that our systems are going to encounter in the world. But I decided and I also really just love the talk that just finished because I think it really shows how we need to think about the long tail and the just incredible variety out there in the world. This talk is going to be about statistics and about a very specific problem that real world systems need to confront, which is just how to set alarm thresholds when you're using anomaly detection. And this is joint work with my graduate student, Silu, Alan Fern, Rishit Garapalli, Dan Hendricks, and C is also jointly supervised by Professor Debashis Mondal in the Department of Statistics. So when we are working on techniques for detecting adversarial attacks or open category classification or out of distribution instances, one family of approaches calculates some score about how suspicious we think things are, and assigns an anomaly score to that point. So when we get a query X, we run it through some kind of a detector or scoring mechanism. We get a score, and then we have to threshold it against some threshold tau. And if it exceeds that threshold, we're going to raise an alarm and say, we think this is an attack. So I'm looking at the test time evasion attacks rather than the training time or poisoning attacks. If it's less than the threshold, then we can go ahead and classify it with our classifier. Now, in practice, we have to decide how should we set tau. And one thing we could have a couple of different goals. Let me just talk about those here. So along the horizontal axis here is the anomaly score for a problem that I happen to be working on right now with the open category detection. And the vertical axis is the probability density. And the blue curve is the probability distribution or density of anomaly scores for my known categories. And then the red is for my novel categories that I did not see during training. Now, there's a lot of literature that tries to set a threshold to minimize the number of false alarms. So that would be setting a threshold here, right? And you'd bound the error under this right tail of what the anomaly scores were for your normal data, for the non-adversarial data. An alternative goal, which is the one we're interested in, is trying to set a threshold down here to bound the probability that we will miss points that are actually attacks, right? So we're trying to bound the number of missed alarms instead. Now, one advantage of trying to do the former, of minimizing false alarms, is all you need to do is estimate this blue distribution. And because you have your training data, you can use cross-validation techniques or what have you to estimate that. I'm a fan of conformal prediction, which is probably a very nice way of doing that. But if you don't, if you're interested in the red curve and bounding the tail on the tail of this red curve, well, then you have a much more difficult challenge, because you need to have training data that's labeled with these anomalies that you've never seen before. And in some sense, you just can't get that. So question is, well, can we set tau statistically somehow? If we had the, now let's consider the cumulative distribution of our anomaly scores. And if we had the CDF FA, which is the CDF of our aliens or our anomalies or our attacks, we could say, well, give me I'll set tau such that I'm capturing, 95% of the alarms, or in other words, I want the 0.05 quantile of this distribution. Now, I do note that this assumes, it requires us to make the assumption that the anomaly scores come from a well-defined distribution. That's a little bit weaker than assuming that the anomalies themselves come from a well-defined distribution, because we're only worrying about their scores. But it's still a questionable one, and one we need to keep in mind. But if we want just to define our goal as detecting 95% of the attacks, that only makes sense if we can talk about a distribution over attacks. So almost from the way we're formulating the problem, we are making this statistical assumption. Okay, so how can we estimate this CDF? Well, one way would be to collect labeled training data of these anomalies. So let's say I can get labeled training data of adversarial attacks or open category queries or out of distribution instances. Then obviously I can compute their anomaly scores, which I'll denote by SA for a sample of anomaly scores. And then I can fit an empirical CDF, and then I can choose the threshold. But of course, this does require getting this labeled sample, and that can be hard to acquire in the wild. So several people have instead suggested a more of an unsupervised alternative. And this particularly comes up in a sub-literature in machine learning called the positive unlabeled literature. But it's a slightly different setup than here. But the idea is that we can go out and collect a sample of clean data. This is the data we are training our classifier on. We can collect mixture data. And this is the idea, is to get an unlabeled sample of data that is a mix of clean data and also attacks or anomalies or open category queries, but it's unlabeled. And the thought is, well, maybe this is easier to collect. And then what we want to do is calculate the anomaly scores for those two data sets, and then estimate their cumulative distribution functions, F0 and FM. So F0 is going to be the clean data, and FM is this mixture. So M, the subscript, denotes the mixture data. And now it turns out we can get an estimate of FA by observing that the mixture distribution is going to be some mixture of the clean distribution and the anomaly distribution with a mixing proportion alpha. So if we could obtain estimates of F0 and FM, which we have, and an estimate of alpha, then we could plug into this formula and get ourselves, by solving for FA, get ourselves the estimate of FA we want, and then we could threshold it. So that's the basic plan. There's only one problem, which is that alpha is not identifiable. So it's pretty straightforward to prove that there is no way that can estimate alpha with any guarantees, like fixed sample size guarantee. But if we're willing to make some extra assumptions, we can get around the identifiability problem. And one approach is a general strategy, which is to not exactly estimate alpha, but estimate something that is a fairly tight lower bound on alpha. And the idea is the following. We're going to set alpha, our estimated alpha, to the smallest value of gamma, where we're going to vary gamma in the interval 0, 1, such that there exists a probability distribution Q such that the mixture distribution PM is equal to 1 minus gamma times P naught plus gamma times Q. So basically, we have this formula, right, that we know from the mixture assumption exists, and we want to find the smallest value of gamma that satisfies this equation, basically. So for which Q is valid. Well, what would it mean for Q to be valid? Well, here's an example, again, using the same anomaly scores that I showed you before. If you plug in different values for gamma and then compute the estimate for F hat A, the anomaly, this is the anomaly CDF here, then if you use a gamma that's way too small, right, I generated this data with alpha equals 0.25. So 25% of the data points are these adversarial attacks or open category queries. And if you use one that's too small, your estimated CDF goes way negative, right? I mean, it's down to -3. And of course, to be a valid CDF, it needs to be between 0 and 1. So the idea is we're going to gradually increase gamma until we get something that's a valid CDF that's always above 0 and between 0 and 1. Great idea, except that because of sampling fluctuations, it never happens. Even when we set gamma equal to 0.4, this curve dips below 0 here. It's just, you're subtracting two curves that are quite similar to each other, and because of sampling variability, the subtraction can go negative. So it doesn't quite work. But in an important paper by Patra and Sen in the statistics literature, it hasn't been picked up a whole lot in the machine learning literature, they propose the following strategy. They say, compute your estimate. So you get this black curve here, which is our estimate, and then apply isotonic regression. And some of you may be familiar with isotonic regression. It finds the least squares fit to the data that is monotonically increasing. And we typically have to clip it at 0 and 1 to turn it into a valid CDF. And so we'll call that F check. That's the little check sign there. And now we look at the Euclidean distance between these two curves and call that D of gamma. And the idea is that we're going to try to minimize the Euclidean distance between these two curves, or at least stop when that distance gets small enough. So in their paper, they prove that, that their estimator alpha naught, which is basically the smallest value of gamma, such that the distance between these curves is less than some universal constant divided by the square root of the sample size times gamma. So they prove that, that this is a good estimate, but they don't tell you how to calculate C sub n, unfortunately. It's one of those proofs that just says there exists a constant. It depends on the sample size, but otherwise we don't know what it is. So they propose that you draw this picture, which is we're plotting the squared Euclidean distance between the estimated F hat and its isotonized correction. Multiply that by gamma, and you get this blue curve. And then they say, well, look for the elbow in the curve, and maybe calculate the second derivative to help you find the elbow. Well, this isn't an algorithm, so it fails from a computer science standpoint. And so when I plotted my data, I didn't see any kind of elbow in my data. So I had an idea. So this is the actual little piece of novelty. It's a completely unpublished work, and it's also very tentative. But the idea was maybe we could find a resampling strategy to assess the sampling distribution between F hat and F check. And so the idea is that we could suppose that that we've got the right value of gamma. If gamma were 0.15 in this case, then that red curve would be a really good estimate of the CDF. And if it's for the anomaly scores. And so we could draw bootstrap samples from it by sampling points in the 0-1 interval here, and then finding out what data point corresponded to that on this empirical CDF here. And we would get an anomaly score like this. And so we could draw, say, 100 or 1,000 of those samples, and then estimate and for each one, we could recalculate F hat and F check on these bootstrap replicates. And then we could calculate, say, the 25th and 75th quantiles of the distances, So for each bootstrap replicate, we're going to calculate this d sub b, the Euclidean distance between f hat and f check, calculate the quantiles of that, and then choose the smallest value of gamma such that the distance falls in that range. And visually, it looks like this. So these are for various values of gamma, or which are candidate values for alpha, right? These are the interquantile ranges or interquartile ranges of the distribution. And bingo, when d gamma falls inside this is right at 0.25, or right around there. So, this looks like it might be a promising estimator. There have been others in literature, and one of the ones that I think is the best that's already out there comes from Ramaswamy, Scott, and Tiwari. And Clayton Scott at Michigan has really looked at this problem in a lot of detail and lots of problems in its surroundings. So I highly recommend people read his papers. And what he does is basically use kernel mean embedding to address this problem. And so I don't have a lot of time to go through this, but basically he can set up an optimization problem where you can solve for this distribution by solving a quadratic program. And he gets pretty good results. This is his method is this red curve, and these are 4 competing methods. And this is the error in finding the optimal value of his mixing parameter, which is lambda. Okay, well, suppose now that I have an estimate for alpha. Now, how can I set the value of the threshold? And now I'm going back to work that was published at ICML 2 years ago by Siliu, Rashid Garipalli, myself, Alan Fern, and Dan Hendricks. And what we did was you choose a target quantile, Q, say we want to do 0.05 for Q, and we choose as our threshold the rightmost point where the empirical, this is again the f hat sub a, our estimate of the empirical distribution, where it crosses this line. So in here, it crosses it 1, 2, 3, 4, 5, 6 times or something. But the last time, that's the one we'll use to set our threshold. And then we're able to prove a theorem that says that this algorithm will return a threshold that achieves an anomaly detection rate of at least 1 minus q plus epsilon. So we have a measurement or a sort of approximation error here with probability 1 minus delta. So a pack type guarantee, as long as the sample size exceeds this amount, which is basically big O of 1 over epsilon squared, 1 over alpha squared, log of 1 minus delta, or 1 over delta. So it has the usual 1 over epsilon squared dependence that comes from using these concentration bounds. And it relies, in this case, on a concentration bound for the convergence of empirical cumulative distribution functions to their true values that comes out of a nice paper by Massart from 1990. So now, if you really want a guarantee, let's say we want a guarantee for that we will detect, say, a 1 minus, I don't know, beta of the points, and I have a certain amount of data, then I can figure out, I set beta equal to q plus epsilon. From n, I know what epsilon has to be, so then I can choose a q that will give me that guarantee. Well, if we don't know the exact value of alpha, any upper bound on alpha works. So you can see there's a problem. From a theory point of view, we need to know alpha exactly or an upper bound on it, but what we can get experimentally is a lower bound. So the 2 pieces of theory do not come together with an overall guarantee. But assuming we can get a pretty good estimate of alpha, I think this algorithm for choosing the threshold is a good algorithm, which we see experimentally. So let's look at experimentally. One other thing, I guess, is we've done some more recent work where we asked the question, in our previous work, we assumed that we had 2 samples of the same size. So our clean data was of size n, and our mixture data was of size n. But what if we can draw those, suppose we have an overall budget of n, but we want to use maybe different sizes for those 2 samples. What's more important? Should we get more clean data or more mixture data? And so it turns out, from theoretical considerations, we want to bound the distance between our empirical curve and the true CDF. And it turns out we can do that by bounding this. This is an upper bound on that. and we can turn this into an optimization problem. What's the best value of n sub m, the number of mixture data points, and what value of delta should we use for our confidence, given that we have an overall confidence budget and an overall sampling budget. And C was able to prove that this is a convex problem, and it remains convex even if we just focus on choosing epsilon, or choosing delta. And so then she's able to numerically solve for this, and we get the following results, that if alpha down here on the bottom is the true proportion of attacks or anomalies in your data, then as it goes to 0, the ratio, half the data points should be from your mixture data. But as it gets larger, then the fraction of points that should come from the mixture data increases until it hits 1, when all of your data is attack data. And this over here is going to be your approximation error epsilon, basically. Okay, and so then we studied 4 experimental questions. We wanted to know, if you use this algorithm for choosing tau, how good is it? The second question was, how loose is the theoretical bound on the sample size? How good are the recall and the false alarm rate in practice? And what is the impact of using an overestimate for alpha? So the first question was, how accurate is our threshold? And another way of saying it is, if we choose our threshold using this method, how big is the gap between the empirical recall, we call it recall here, but the fraction of attacks that are correctly detected? How big is that gap, and the target value we wanted, which was 0.95? And that gap is basically the epsilon in the theory. And so what we're doing across here is for different values of alpha and different amounts of data, what does it look like? So when alpha is very small, you need a lot of data to get close to the target. But as alpha gets bigger, you need less and less data. And so when alpha is at 0.5, you need relatively little data. 100 data points will suffice. So this is with some synthetic data. If we can also ask, how loose is the bound? And of course, the answer is very loose. So the way we get this plot is, this is the actual amount of data we had, and this is the amount of data that and from that amount of data we calculate our actual observed error rate, and then we plug that into the theory and ask, well, what would the theory say we needed? How much data does the theory say we need to get that same error rate, right? And so, you know, in practice we have 100 data points. Theory says we need 10,000 up to 150,000 or something like that. So there are several orders of magnitude difference depending on alpha between what you need in practice and what the theory tells you. So not surprisingly, the theory is loose here. In terms of recall on UCI data sets, using the isolation forest as our anomaly scoring mechanism, we see that for some data sets, we're able to really completely hit the target. For others, particularly the letter recognition and the OCR data sets, we're quite low for small values of alpha. And our false positive rate or false alarm rate is non-trivial. Again, small values of alpha tend to have false alarm rates in the 10 to 25% range, except for the cover type data set. We love the cover type data set. And finally, what's the impact on if we use a value of alpha that is too big? Even by a very small amount, what we see is that the blue dots show what happens to our recall, our missed alarm rate. It increases relatively modestly, but our false alarm rates really shoot up as our estimate of alpha goes is not tight. So to complete then, to summarize this, what I've tried to argue is that in a lot of our systems, when we deploy them, we have to choose a threshold against some kind of a score that's a score of for detecting adversarial queries or out of distribution queries or open category queries. And if we're willing to assume that the queries follow a stationary distribution and that we can model that, then we, and particularly that the scores, the anomaly scores follow a stationary distribution, then we can model the problem as a 2-component mixture model, where there's one component that's known from our known data, and then there's another component that is unknown from the attacks. And there's an unknown mixing proportion. And then I briefly described two methods for estimating alpha, although there are some fundamental challenges with doing that. But I think in practice, we'll have decent methods for that purpose. And then I reviewed our theory that gives PAC guarantees for bounding the missed alarm rate for detecting adversarial attacks, assuming that our estimated alpha is an upper bound on the true alpha. And of course, in experiments, we see that our observed anomaly detection results are much, much stronger than the theoretical guarantees. So this was funded by a variety of sources, including Elon Musk, a gift from Huawei, the National Science Foundation, and DARPA. And here are the references that I discussed. And with that, I'll stop and keep us on schedule.
Hi, Tom. Thanks for this great talk. Let me share the screen. Can you guys see the screen now?
Yes.
Okay. So yeah, now we move to the panel discussion. And yeah, we provide two ways for asking questions. The first is that you can directly use Zoom to put your questions there. And you can also like raise your hand, put the question there, and I will unmute you to let you ask the questions. And also you can like scan this QR code to go to the Slido website and put your question there. And I think, Xinyu, you have some question first, right?
Yeah, so I will start with a question for all the speakers. So in this afternoon, we heard about, I think that all the talks are kind of related to some perspectives of potential issues for deep neural networks. For example, we heard about like adversarial samples and also like predictions for out of distribution samples and also like some backdoor attacks. So one question is that, do you guys think these kind of issues arise from the kind of a bias of the training set, or is it kind of the potential problems of current neural network designs? Like if we want to like improve the model's robustness against this variety of these kind of issues, then what could be the most important steps to move on? So who wants to like answer the question first? Maybe Lawrence, you can go first.
Thanks for putting me on the spot. I mean, this is that's a difficult question, right?
Well, if Alex Madry were still here, he would say that it's inherent in the that there are these other aspects of images that are valid features that we as humans don't see, but that our adversaries can manipulate, right? At least that's my interpretation of the bug features not bugs paper. Mm-hmm. Do I have that right?
Yeah, we kind of know a bit about it.
So that seems that it's kind of inherent in working in computer vision. So I think that means we need to find ways of, as Alan Ewell was saying this morning, of getting our computer vision systems so that the things they see correspond to the things we see, right? And it's clear we have a long ways to go because there's quite a divergence between what our DNNs are looking at and what we look at. Mm-hmm. But I don't have any particular ideas. Does anyone else on the panel have ideas about how to I don't know, constrain or control? I guess Bo-Ching was talking about changes in the architecture, basically.
Yeah, thank you for. That's indeed a very tough question. But to make the discussion maybe more interesting, I just make a guess. I think, kind of like a bet. I bet that it's not due to the training procedure or training data. It's because of the existing architectures of neural network. So if we see like using Lipschitz continuous network, it's guaranteed that the small input will not be amplified to too big activations and the output. So it's guaranteed, it's certified, robust, but it's not accurate enough. What if we maintain that constraint and using some, instead of manually designed, try to do the search, maybe we could find a better network, which is guaranteed robust, I mean, will give you high quality prediction results. So that's my take. I think it's because of the neural network architecture right now.
Yeah, so I agree with Botin. I think we can make a very shallow network, like a one layer linear network. Then we can just exactly compute the lineages, but it's probably not powerful enough. So, but I think it's the long tail distribution in the data maybe also plays some role according to your talk, right? Because that may introduce some other problem, I guess. Yeah.
Yeah. So sorry. Yeah, sorry to cut you. So for me, I have two parts of me. The one part of me is very optimistic. So I think with more people, involved in doing research and kind of rethink about the design objective of neural nets, right? Instead of pursuing accuracy, we also want some notion of robustness or even ethical constraints embedded in the neural net design. And I think the performance and the certified performance can be improved somehow. But if eventually we want to eliminate, for example, adversarial examples, then basically we are asking us to build a human-like perception system, right? Because all these adversarial examples exist because humans do not agree with machines' decision. In that case, if our final goal is to eliminate adversarial examples, and that basically means to build a human-like or human equivalent perception system, I think there is a very long way to go, and neural nets alone may not be sufficient to achieve that ambitious goal. Xinyu, I think you are saying something, but you are on mute.
Yeah.
Oh yeah, yes, yeah. So I unmuted Terry, so I think he has a question. So would you like to ask your question?
Sure. It's a question. Well, first, great talks for everyone. But my question is first towards Tom, and the rest of the panel might chime in. So in doing your analysis, you talked about stationary, but do you need to assume that the distribution of adversarial scores are actually generated from independent observations? Because in lots of the real issues in nature, but also the machine learning adversarial stuff, they're not independent scores. They're actively trying to defeat the system, in which case you lose the independence assumption, which I think also is necessary for your theorems, although I haven't read them in detail enough to be sure. And does the rest of the panel think that that level of independence makes it much harder, or lack of independence makes it harder for us to analyze?
Well, so the stuff that I described requires that the anomaly scores have a well-defined distribution. So yeah, and then we're trying to bound the probability of failing to detect an attack or an anomaly. So, but I think when you're more in the cybersecurity kind of setting, that's not going to work, right? You need to have some sort of more of a minimax robustness constraint instead, right? So I think for open category and out of distribution, it's probably reasonable, but in the adversarial case, now it's an interesting question. If you're looking at some indicators of the distance of, that gives you some indication that the query is adversarial, some measure of adversarialness, then maybe those scores look like they come from a reasonable distribution, and you could look at their CDF. But I don't know. I haven't looked at even what the standard attacks produce. So maybe someone else on the panel might have a sense of that.
I actually have a follow-up question to that, to Thomas, if I may call you that. So it's the score distribution provides somehow a smooth analysis to the adversarial examples. So all the existing work when they try to certify the neural network, they certify the worst case. But if we assume actually a well-defined distribution over the score, maybe we can get a better improved analysis about the robustness to certify that in a smooth way. I wanted to see if you have some comments or some idea to share on that sense?
Well, let's see. If it were a white box attack, then the adversary knows how we're calculating this score too. So then it becomes an issue of how hard is it for them to drive the score down below our threshold tau. And I haven't analyzed that, but yeah, you know, knowing how good the attackers are, they can probably find a way. But it certainly is an interesting question that turns it from a binary question to a continuous one, as you say.
To take the expectation. In expectation, what's gonna happen when there is a white box attack instead of the worst case?
Yeah, and I don't know, but it seems to me that if we want to have a guarantee against an adversary, it has to be more of a minimax guarantee that you know, the best they can do, we can still detect because we have a big enough balls around our images. But the trouble is those balls are not LP norm balls. They've got to be something in the visual space, which takes us back to the first topic. Yeah.
Yeah, thanks for the discussion. I think we unmute Xu Yuwang. Would you like to ask your question?
Yeah, okay. There are two questions. First question is, I consider, so for the interpretable deep learning technique, we want to know how does deep learning work. Can this technique help for the defense against the adversary attack? That's my first question. Yeah. And the second question is that we know for the base learning, okay, like the deep gauge processing, it can estimate that, so the uncertainty estimation to give the mean or variance. So can this technique is robust to adversary attack? Okay, this is my two questions. Thanks.
Can you're muted.
Sorry. Yeah, so I can answer the first question regarding interpretability. So the short answer is no. So at least the current interpretability methods are not robust enough to detect or adversarial example. So people have demonstrated that this interpretability can be under fire. That's literally the title of one paper. And basically they show two types of attack, right? One way is you can manipulate the interpretability maps like a CAM or whatever while keeping the prediction constant. So basically you can add noise such that you can generate whatever interpretation you want. Or you can keep the interpretation map the same, but change the prediction target at your desire. So in either case, these interpretability tools are very fragile. But that being said, our recent ICML's publication actually showed if you use a proper interpretability metric, basically you try to make multiple classes to have the consistent interpretation, then using that as a regularizer to train a neural net can actually make the neural network robust, and the robustness is very similar to the performance of adversarial training. So it depends on what notion of interpretability you are using, and you have to use the right interpretability metric to improve robustness. So they are certainly connected, but it's not for free.
Okay, the follow-up question is that, so can we visualize that adversary attack samples to understand how to attack that model?
Yeah, but if the visualization can be fooled or can be deceived, how can you trust that visualization? That's the deeper question. Consider a white box setting where attacker knows you are going to use certain interpretability tool to visualize and to do detection. I can devise an adaptive attack to bypass your detector or your visualization, right?
Okay, thank you. Yeah.
So actually we used to conduct some experiments on MNIST. So basically for larger perturbation, you can actually show there more on the central pixels in the image instead of the boundary pixels. So there's some interpretation of that, but yeah. But usually for like more complex images like CVPR or ImageNet, it's more like a very small high frequency noise. So it's very hard to really know what it's doing for MNIST, it's relatively easy. Yeah.
Okay, thank you.
And for your second question, so I don't. So for Bayesian learning, I think it's some paper, including one of ours, report it can somehow improve the robustness, but I don't know the reason. So one of the reason may be because you're doing the sampling, so it's actually trying to smooth the landscape of your function. But we don't have any good theoretical reason for that. Yeah.
Okay. Okay, thank you.
Yeah. Thanks.
Okay.
Okay.
Yeah.
Go ahead.
So thanks for asking and answering these questions. And we have another question here for Lawrence and Bochin. Like both of you guys mentioned, like deep networks are, or like human vision systems are kind of poorly generalized to some auto distribution or say long tail images. Like, do you think this, like for our models to overcome these problems, should we consider this from the, like say the architecture design, or say the like Marjorie said, like enrich our data sets, or we should consider both to make our network more generalizable? Maybe Lawrence, you can answer first.
Sure. Yeah, I mean, it's probably a little bit of both, right? Like I think sort of the thing that I've been struggling with a little bit with sort of the adversarial robustness field is that, it's really easy to break our systems, and you really don't need to, compute any gradients or anything like that, right? Like if you sit down for like half an hour and you open, Paint, right? And you can come up with gazillions of ways that will, are sort of guaranteed to break our systems. And so to me, sort of the sort of learning settings that we have chosen, right, or like some of the assumptions there, they seem a bit arbitrary from the security point of view, right? Like they may still be interesting from the understanding properties of our model point of view, although I'm not sure whether we made a lot of progress there. But from a security point of view, like I'm not super convinced. Then there's the question of okay, how do you make these systems more robust, right? And I'm a little skeptical that we'll really sort of be able to solve this problem, because I think in order to really solve it, I think as you alluded to earlier, I mean, you basically need to exactly reproduce the human visual system, and if you don't, then you're always going to be able to find images that are classified differently by the model than they are by human annotators. And so it's a matter of like, well, do you believe that we can pull that off? And I'm a little skeptical, at least in the short term. Making predictions beyond let's say 10 years is always hard, of course. There is a little bit of evidence that sort of data-driven approaches can help, right? So we had a paper in ECCV 2018 where we pre-trained models on 3.5 billion images to predict hashtags for those images, and then we would fine-tune those models on ImageNet. And there was a paper, we released those models, and there was a paper later, I forget who the author was. It was, I think, someone at NYU, but I can look that up later, who basically did analysis on data sets like Thomas's ImageNet C and ImageNet P data sets, as well as adversarial analysis. And their results suggested that sort of inherently these models that were trained on these massive amount of images had more robustness to all kinds of perturbations, right? So there is some evidence that a data-driven approach can help. I don't think it's going to be enough, right? So like sort of the amount of data that you'd need to scale with, is more than there are images in the world, probably. And so I don't think that's going to be sufficient. So there has to be something on the modeling side as well, but I don't know what it is, right? Like if I knew, I'd be working on that right now, because it'd be the next big idea. I don't know if that answers the question. Maybe Bo-Jing, you can add to this.
Yeah, sure. Also maybe try to make the discussion more interesting. My gut tells me maybe it's not both. It's actually on the model design side. Let me maybe try to explain why I had that feeling. So the data side, people, including Lawrence Yao paper, we can try to feed the model not only label data, but also massive amount of unlabeled data. So we can have a better kind of estimation or approximation of the data manifold and the training stage, hoping the model see the manifold, full manifold, it becomes more robust and testing stage. This idea has been there around for a while. People have been using different techniques to better approximate that manifold by adversarial examples, by unlabeled data, by mix up. All the results we have seen so far, I think they can improve the model's robustness, but really it's still far from solved, as you said in the slides. So also recently there is one ICML paper, sorry, forgot the authors as well. They mentioned there is a intrinsic trade-off between robustness and accuracy under certain conditions for neural networks. So it's really hard to achieve both by the existing model architecture design. Therefore, my gut is, I feel actually in order to solve this problem fundamentally, we need a better model design. Maybe not actually a neural network, could be a mixed model, mix of neural networks and some other like the models Cho presented in his slides. Time will tell. Yeah, I don't know, but that's my feeling, and time will tell if I was correct or wrong. Let's see.
Okay, yeah, thanks you guys for answering this question. Xinyu, I think you got another question, right?
Yeah, so Wei Bin, I mute you, so you can ask your question now.
Okay, thank you, Xinyu. I have a question that I want to ask for Qing. So, in your opinion, how is the adversarial robustness related to the problem of domain adaptation? So, in other words, can the task of achieving adversarial robustness be viewed as a problem of domain adaptation? Thank you.
I think the answer is a definite yes. Adversarial training, from my perspective, I think is a domain adaptation problem, because you generate adversarial examples in the training stage. You try to make the model invariant to those examples. So it's basically the same idea as learning domain invariant representations in domain adaptation. So in that sense, it's one connection. Second connection is you can check our CVPR paper this year. First author, actually, Zihang is here. We showed when we train the models, we count two branches bench normalization, one for clean data, the other for for adversarial examples. Actually, we can improve the model accuracy. So also the two branches of bench normalization is also a very typical technique in domain adaptation. So when we train the model, one kind of path of bench normalization, but on the targeted domain, we try to re-estimate that statistics of the estimation. So a very simple technique, very effective. It's almost become a standard trick in all the existing domain adaptation methods. So that's the second connection. The very last connection is regarding, so recently the generative models. So people tried to use the gigantic generative neural networks as image prior to do the regularization or to do the constraints in the downstream tasks. It has been proven effective in domain adaptation. And I see also recently some defense methods, they also use that prior. So they don't retrain the generative model anymore. Instead, they use that as kind of pre-trained, very powerful generative model as image prior to clean the adversarial examples. In that sense, that could be, you can consider that as the third connection. So what other connections there will be, it's really, I'm very hopeful that the community will discover more and more and try to actually improve the robustness and also benefit on the other way around, benefit domain adaptation as well, by moving these two fields forward.
Okay, I see. Thank you.
So our next question is about the verification of these models. So in Professor Achori's talk, he mentioned about the verification of decision tree models or some k-nearest neighbors. I'm wondering for example, suppose we want to scale up these techniques for more complex deep neural networks, then what could be the potential directions to go? I guess all of you guys can discuss about this topic.
Yeah. So so verification for neural network has been there since I think 2018, and there are most of the work try to approximate the nonlinear activation function. So because the main difficult, so if it's linear neural network, then it's just a linear thing. So it's very easy to verify. So the difficulty is the nonlinearity, and most of the work try to approximate its lower bounded and upper bounded the nonlinear activation. So the technique is quite different from what I talk about the nearest neighbor today. But there are some similarity in the sense of the primal dual relationship. So this is actually coming from the neural network verification. So attack and verification can be think of the primal and dual. So attack is trying to find the primal solution. The verification is trying to find a dual solution, which is the lower bound of your minimal perturbation. Yeah, that part is there are some connection. Yeah. But and for more complex thing like how to combine different structure is probably very hard. Yeah. So one of our goal in the beginning is try to, because there are some paper proposing nearest neighbor classifier can help the robustness of neural network. We try to verify whether we can verify this kind of neural structure, but currently it's not very successful.
Yeah, I want to echo Joe's comments. So basically, this verification method suffer deeply from this curse of dimensionality. So the larger the network, the deeper the network, the looser the bound you will get. But that being said, our recent CVPR paper, we discovered something very interesting, right? So if you look into the attack model, you assume, for example, this rotation or like a brightness or contrast change to cause the semantic changes in the image. It may incur large LP norm perturbation. So it seems at first place it's hard to certify. But if you look closely, these semantic changes are actually governed by a few low dimensional factors like rotation. You just change the degree of the images, so on. So if you try to certify the underlying parameters, that problem is actually more tractable. Rather than try to certify the changes happen on image space. You try to certify the changes happening on the parameter space that controls the semantic changes. In that case, we found out that this certificate can actually be tight and more scalable to large networks.
Yeah, thanks a lot for your answers.
Yeah, could I ask the panel, the other folks on the panel, what people think about the probabilistic smoothing, which is an alternative for getting guarantees?
Yeah, I think it's also very nice. It's nice in a sense you can take a black box model and then do the smoothing. Yeah. But I think there is so that's good, but there is problem in the sense of you need a lot of inference time. So in the inference time you need to like do maybe 100 times forward propagation.
How much does it damage your classification accuracy?
It's better than other certified training algorithm. Yeah, because it's like you add a random layer in the beginning, so if it's small and this doesn't hurt too much your accuracy.
Yeah, so there is again a trade-off. If you want to certify more, then that means you need to add a Gaussians with more with larger variance, and larger variance will decrease the accuracy on the clean data. So there's always a trade-off between certification and standard accuracy as well.
Hi, I have a question for Dr. Lawrence van der Meten. First of all, I think your talk is really brilliant and really shows another perspective about adversarial machine learning. And my question is, because you mentioned like the machine learning systems are actually biased towards different data sets, but on the other hand, the human perception also is kind of biased towards different data sets, like in different countries or regions. So does that mean you think that human perception and machine learning systems are somewhat highly similar in this sense?
I don't know if they're similar. I mean, you know, arguably human systems also have their issues. You know, a lot of which are under discussion in the US these days, I guess. I mean, maybe the difference is that for, you know, computer vision systems, it feels like a much more, you know, easy to solve problem, right? Because you know, at least for sort of things like cultural biases and I mean, those are one example, right? But also, you know, there are biases in sort of what classes do we choose to recognize and which one do we, you know, not choose to recognize, right? Like those kinds of biases seem, you know, easier to resolve than the biases that maybe humans have, right? Because solving some of those would, you know, I guess require, you know, people to travel to every country to, you know, see things for themselves, which may not be quite practical. So I don't know if humans and computer visions are similar in that sense, but I do have a strong sense that at least in computer vision, you know, we should be able to do better with a relatively modest amount of effort compared to the amount of effort that we put into other problems. But I don't know if that answers your question.
Yeah. Thanks, Lawrence. I think that answers my question perfectly. Thank you.
Okay, I think we are running out of time here for the panel discussion. And thanks, Lawrence, Pinyu, Chu, Boqing, and Tom for attending this panel discussion. Thank you so much.
You're welcome. It was a lot of fun.
Thank you.
Thank you.
Yeah, thanks a lot for the great discussion.
Thanks.
Mhm.
We next then move to the second poster session. Again, like you can find the Zoom link of each poster at our internal website of the CVPR workshop. And yes, again, like all papers will attend this poster session. So enjoy. Thanks.